Okay, everyone consents to the recording. Away we go. Welcome to the P2 Live Forum. Today is March 30. It's 1:00 p.m. Pacific in California, and it is 4:00 where our guest presenter is, Dr. Gavin Garner. And before Gavin gets started, let's just go over a few things while more people roll in. When Gavin's done today, we'll have a very short catch up on the Visual Studio Code extension for Spin2, which now includes debug. So Stephen will show us that. He's here. Thanks, Stephen, for all your work. And then also, where do these videos live? I watched the video from last week, and towards the end, there was some friendly squawking about where the videos actually live. So they're on the Parallax YouTube channel. And I try to post every single one there. Occasionally I will miss, which may have been the case lately, but definitely alert me to that. So at the moment, there are 77 videos here, and it's under a playlist. Really, if you just go there and click around, you're going to find them. But the playlist is called the Propeller 2 Early Adopter Series, because we've not actually truly formally released the Propeller 2 yet, because our Spin 2 documentation is not yet done. So when you head over to YouTube, you'll find them, long list of them. Usually the newest one is on top. So yep, they're out there. And I think the question really revolved around, why am I not updating the Propeller 2 forums with the location of the videos? And it's just a function of time. It becomes an awful lot to maintain the same thing in 3 places. So if everybody can just kind of get used to a change of your procedure and go to YouTube to find them, that'll be really easy. So the forum link will probably not be updated too much in the future. And I posted this story today. This is about the P2 Edge and the Edge 32 megabyte RAM version. And we were getting ready to build more of these, and suddenly the parts we had on order vaporized and right in front of us, and were replaced with a 1-year lead time, which is pretty much normal for a lot of everything we're doing these days. So if you get P2 Edge keychains in your order, you will know why. The boards are in progress, they arrive, and rather than throw them away, we put key rings on them and send them to you. And if you want to secure some P2 Edges, there are actually 6 left in stock right now. And you can buy them, and we won't have any for, I'd say, about 6 weeks, unfortunately. So we redesigned the circuit board and ordered all new parts. We're able to get it all together. And this is kind of what we're up against these days. So it's just crazy.
And a quick question. Is the 32 megabyte version in the store? I didn't see it. The reason I'm looking for it is not to buy it, but to get the data sheets.
It is there. Look under P2-EC32, okay, and it should show up, but they're not, there are some link shortcomings where they're not linked as related products. So sometimes you have to look around.
Okay. Thank you.
Yeah, and you can add yourself to the wait list on each product page, and then you'll get an email notification. But if you're building a product, we don't want to hold you up, and you can submit a purchase order to hold parts, or if you're just in a dire situation, like happens all the time, and somebody just needs 1 or 2, usually we can find them in our office and scrounge around and take care of you, or other customers can help out. So you're not totally out of luck here. Yep, Ari just posted the link. Thanks, Ari. And also, we released last week the beta version with debug support and the Propeller tool. And I don't think we've had any feedback saying it's not working. Funny thing is, it only didn't really work reliably on the developer's computer because he has so much USB stuff installed, but I think it's working for everybody. So go out there and grab it. There is a video that shows you what's new with that, and I'll post that right now in the chat, and you can check that out too. So today we have Dr. Gavin Garner. We call him Gavin, and he's been a Parallax customer and educational user of our products for many years. And I'll just give you a brief bio background of him, since he has a really interesting history. So as I mentioned, he's an early adopter and user of the Propeller 1. He's used the basic stamp in classrooms for many years. He grew up in Richmond, Virginia, graduated from St. Mark's School in Boston, then ventured to Colby College in Maine, where he majored in physics and minored in music. Returned to Richmond, spent over a year working as a mechanical engineer for AMF Bowling. That's right. So at their worldwide headquarters in a place called Mechanicsville, which seems to really exist. And at AMF, he made improvements to the pin spotters. Those are the machines that automatically reset the pins at the bowling alley. And so he obviously loves mechanical stuff of all kinds. He went back to the School of Engineering and Applied Sciences graduate program at UVA, worked as a teaching assistant for various undergraduate courses every semester, and enjoyed everything he was doing there. He has received a whole bunch of awards, too long to list, and he probably wouldn't talk about them himself, but I think they're very important. They're on his website. And he's earned his master's and PhD degrees in both mechanical and aerospace engineering. So I will let him tell you about all the things that he does, because it's really neat, but it represents a combination of everything Parallax loves, which are microcontrollers, education, mechatronics, and truly teaching students. And I can tell you, after having looked at his midterm that he sent to several of us at Parallax several weeks ago, that he truly asks students to learn. They're writing their own code, and he's teaching them architecture, coding, and then all kinds of tools. The number of tools in his lab are astounding. So I can only imagine the software licenses and keeping them running and just remembering how they all work is equally astounding. So with Gavin, we are working to produce a mechatronics book, which is his curriculum, which we expect to make totally free. And we will also make a parts kit to go with that other programs can adopt as their own. So hopefully I didn't give away too much of what he's going to talk about, but I just wanted to be sure those things were covered. So introducing Gavin. Thanks for coming back, Gavin.
Thanks for having me, Ken. Thanks for that introduction. So for the next hour or so, my plan is to first tell you a little bit about my labs, just because Ken said there were a lot of new signups today that didn't see the presentation I did about a year ago. And that everybody might want to see kind of what we do at the University of Virginia in teaching mechatronics in particular, and I'll describe that a little bit more, exactly what that means to especially the mechanical engineering students, undergraduate students at the University of Virginia. And so, yeah, I'm trying to use this Propeller 2 chip and to teach the concepts of mechatronics, and I find that this chip is just perfectly suited for doing the sorts of robotics applications in mechatronics. So it's a great engineering tool, and it's a great teaching tool. So I can also kind of give an overview of kind of what the Propeller 2 is. I know that there's some regulars here that have been to all the live forums that probably don't need to understand that, but I will go ahead and do that. But I'll start with an overview of the labs. So let's start with a video, sort of a quick run through of what we do. And I'm going to share the sound, but I'm going to talk over it too. All right, so this is just a quick walkthrough of kind of what the hallway looks like in my building on the second floor. We've got a really neat turbofan jet engine. This is a unique kinetic art clock that I built with some students in a group that I founded called the Gizmologists, and they just make cool stuff. So you can see RGB LEDs showing the second, and there's aluminum water jetted gears that do the hour and minutes, and then light shines through them. Of course, these are addressable RGB LEDs. So it's just an example of just sort of a fun project using, in this case, a Propeller 1 chip to make something neat. So again, Rolls-Royce donated this working jet engine, or was working for many years, probably like a $5 million prop, which is kind of cool to show our aerospace students. This is a rapid prototyping lab. So we've got state-of-the-art Stratasys printers, and that's sort of a print center for the whole university to be able to make stuff. And this is the mechatronics lab right across the hall. And this is where I teach the mechanical engineering students how to make their machines come to life in using Propeller 2 chips in this case. You can see there are guitars on the wall. That's another project I do in an advanced mechatronics course, which I'm actually simultaneously teaching right now this spring. So we're making a whole new batch of electric guitars. You can tell the students get sort of excited and creative as they come up with their unique shapes. The more academic side of that is they're using finite element analysis to anticipate the resonant frequencies of the shapes. So they're trying to tune them all in math before they print them out, in this case on a giant CNC router. And then the other more academic side of it is they're building effects pedal circuits, which is one of the things that makes electric guitar such a unique instrument, is that the musician can send the analog electrical signals through all kinds of crazy filters before they amplify it. So those are the students work out their, I'll go back to that. They work out their effects pedal circuits in a program called Multisim, which is owned by National Instruments. And that's basically like CAD software for electrical engineers, where they can kind of simulate all of their analog filter circuits, all their op amps, look at virtual oscilloscopes, and make sure everything works the way they want it before they build it in real life. So have fun with that. I'll talk more about that robot in a second. So I also have a lab down in the basement called the Mechatronics Innovation and Learning Lab, aka the Mill. And this is where I've got a lot of the sort of bigger toys. Like we've got a lot of older dimension printers. Again, those are nice because they print out two materials. So one's a dissolvable support material. So you can really literally make any shapes you want. You're not constrained to geometry. You don't have to pick out the support material afterwards. You just throw in a bath of a sodium hydroxide, or sometimes we just use OxyClean, a laundry detergent, to melt away the support material, and you just get working parts fully assembled. So one of the ways I like to explain this is if you wanted to print a ship inside of a bottle, it's just as easy as printing a ship outside of a bottle. Whereas if you want to make a ship inside of the bottle, it's totally different than trying to make a ship that's next to the bottle. So any geometry is perfectly free on these printers, which is unique. I've also got a large CNC router in the back. That's a ShopBot that can do 8 feet by 4 feet in terms of the overall bed. I've got a little laser cutter in the back right, some other little CNC machines. And we've got such big projects. I've come up with this pallet jack lifter to be able to store them in these blue boxes on the right. That was a major improvement a couple of years ago. All right, so that's the Mill. And stop me if you have any questions. And then I made all these kits, and I'll talk a little bit more about that later on. But this is just some of those people making that kinetic art clock, just as an example of students working in these things. This is another kind of kinetic art thing where they had a gumball machine, also Propeller 1 chips behind the scenes making that thing work. This was a tic-tac-toe bot using a Propeller 1 chip that has basically AI to be able to figure out how to play against you. And it even has some of the War Games movie references where it asks you if you want to play a game, and if you tie it, it says it's an interesting game. Anyway, so this is another Propeller 2 robot using mechanism wheels, and this is actually the base of what we call the Rotundar robot that has the UVA Rotunda 3D printed. It moves around and kind of acts as a tour guide. This was a jet ski kayak that we made, and we actually 3D printed all of these impellers and the casings for them, and it's controlled by a propeller chip, and it can move to steer the kayak as it moves too. And this is it in action. They miscalculated kind of how, for the prototype, they wanted to get to work, but they made the thing that holds it very heavy. So Newton's second law wouldn't let them go all that fast at the end. But it had quite a bit of power for what it was. I gave them my Eddy line kayak to work with, which is pretty light. This was an example of another capstone project where they made this little robot out of water jetted aluminum sheet metal. And they were using these Technic motors. So they're called the ClearPath servos, and they cost about $300 a piece. So they're not cheap, but they act just like stepper motors, even though they're brushless, DC brushless servo motors with absolute encoders inside them. So you can send them just a high or low to tell them what direction to go, and then just send them one pulse, and they'll make a step. But really, it's got all the benefits of a closed-loop feedback control inside of these servos. This is sort of a demonstration of kind of what mechatronics is. We're showing a brand new modern mechanism down at the bottom right, juxtaposed to antique mechanisms, which would work off of just continuous rotation. I've got another demo I'll walk through that explains this a little bit better and kind of what mechatronics is. And this was a prototype for a display at a science museum in Virginia. And we've also used propeller ships for various contests over the years. And even the NASA's robotic mining competition, we built robots around propeller ships for 4 or 5 years for that too. And this was NASA trying to figure out how to mine for water on the moon and on Mars autonomously. So again, a lot of water jet materials. All right, this was an Etch-a-Sketch. I'm just kind of showing some random things we've done with Propeller 1 chips over the years. So this is a Mechie mouse robot. Disney hasn't sued me for that yet, but it's the mechanical engineering Mechie mouse. And let's see. We've also done things like a missile defense system with a Nerf kind of office dart shooter that was controlled by Propeller, and they had to figure out where objects were. In this case, we pretended they were alien flying saucers attacking the lab. So these are students working out spin code to shoot down the attacking things. Is the music level okay, or should I adjust that?
It's good.
Okay. And this was kind of a neat thing I did for many years as a final project. This is a 3D printed printer. So I used the 3D printers to make printers, and then the students had to program these printers with a Propeller 1 chip to act like plotters. And so they'd move a ballpoint pen around to draw whatever pictures the students wanted to try to work out on an index card. So they basically would work out how to program these 3D printed printers. And what's really cool for those educators out there, when you're working off of platforms that are 3D printed, especially on professional grade 3D printers like these Stratasys machines that have the dissolvable support material, if anything breaks, you just hit print and get the replacement part, and like right then you plug them in. So this is one of the reasons why 3D printers have become so interesting to military applications and space. If you got people on the International Space Station and something breaks, just being able to upload a part and then print it when they need it. It's kind of cool. And of course, during the early stages of the pandemic in this country, at least, there were real supply shortages on things like masks and stuff. So one of the things I did was help to make 3D printed masks and mask holders for our hospital workers, just in case we needed them. And because we had lots of extra 3D printable material, but we didn't have the actual stuff we needed. So those would use MERV 15 HVAC filters, which we actually had tons of. So basically behind the scenes on 3D printers is mechatronics. So basically in teaching students mechatronics, we're kind of teaching them how to make 3D printers and how all this works. You can find these videos on YouTube. If you search for me, you should be able to find them, or UVA Mechatronics, they should show up. All right, so that's a quick overview of kind of some of the things we've done in the past. Are there any questions on that so far? All right. Let's see. So I'll talk a little bit about what mechatronics is in general. So this is a quick video I shot this morning that shows off this mechanism wall. And what this is it's another kind of science museum type display, a prototype. And this shows kind of the evolution of where mechanical engineers have come from to get us to where we are. So if you take this first example, this is a Geneva drive. The old paradigm in mechanical engineering is we'd start with a very simple motion, something coming from a water wheel or a windmill or even an induction motor in the last century, where you just have a continuous rotation, a constant RPM motion. So imagine just again a water wheel in a river, and you want to convert that into more useful motions for us. So if you wanted to have that motion start and then stop, so it's an intermittent motion, you might use a Geneva drive, where you've got these white discs with these weird sort of flower shapes, and then you've got a little peg on this little central black gear, and it rotates around, and a little peg goes into a slot to cause the output to rotate, in this case on the right 90 degrees or 45 degrees on the left. So as this centerpiece moves around at a constant RPM, again, imagine it's powered by a water wheel, it causes the output to start and then stop and then start and then stop. So some other examples how we can make fancy motions is to use cams. So these little black shapes are all different sizes, and as these pistons roll on them, this one goes up and down a sine wave, this one goes up and comes down quickly to do a sawtooth wave, this one does a square wave, simply by these shapes. So again, the old paradigm in mechanical engineering and mechanism design was to start with a simple motion and then convert it to more useful motions to really cool shapes. And of course, the math can get very complex as you're trying to model that. So juxtapose that with the modern systems. This is an RC servo motor, which most of you are probably familiar with. On the bottom, pushing this piston up and down, and all it has to do is run a program, in this case running off of a P1 chip, to do the exact same thing as this piston over here using the antique mechanism. So right now, this servo motor system on the right, this modern mechatronic system, does the same thing, and all we have to do is change the program, and now it's doing the same thing as this sawtooth wave one. So just by changing the program, we get this one system to make basically any motions we want. And that's the power of mechatronics, is that once you have software and electronics in the loop talking to these smart motors, changing the motion is as simple as just changing your code. And the extension of this is fly-by-wire. So I've got a linear potentiometer here in the green section. As I pull on this, it's almost like it's a puppet, and I've got an invisible string making it mimic whatever motions I do. So this is a great example of kind of what mechatronics is, as opposed to the antique way of doing this. So back to the Geneva drive, there's a stepper motor above it. And in this case, the stepper motor is making the exact same motions as this Geneva drive on the left. And if I flip the switch, it'll now mimic the one on the right. So I can change if it does an 1/8 of a turn or a 1/4 of a turn as it mimics this just by changing the software. So again, I've got one system that can make any motions I want just by changing software. And that's kind of the secret behind 3D printers. Is 3D printers, typically at the entry level ones that you get for your homes, are running off of stepper motors. And with the power of 3 stepper motors, you can get it to move anywhere within a 3-dimensional volume, the extrusion tip. As you can see, a lot of these parts on this prototype are 3D printed as well. This demonstrates kind of a neat idea. This is an antique sort of brain, and this is a Watt centrifugal governor, and you still find these in small engines like in your lawnmowers. So in this case, imagine steam coming through and powering a turbine that's coupled as output. If you put a load on it, so if the train starts going up a hill, let me back it up a second, then it would bog down the engine, and then the weights would pull down by gravity. If it goes downhill and it goes too fast, the weights pull up from their centrifugal force, and that causes this throttle to starve the engine of the extra steam. So this is sort of an idea of, you know, a way to regulate kind of like a cruise control for a system, and it's purely mechanical. Whereas of course today our cruise controls are powered off of microcontroller chips, or controlled from microcontroller chips and software. So that's an antique brain. This is kind of a neat idea. This is an example of how we used to change speeds. So we've got, again, imagine this being powered off of something simple like a water wheel. So water wheel is powering this gear, and let's say this central gear, and there's an outer gear too. So this one on the left is going to change speeds as the smaller radii and the larger radii switch off. And then on this one in the middle here is missing half of its teeth, and this outer ring is missing half of its teeth. And so they're actually going to trade off back and forth on which one's powering this orange one, so that can switch directions. So we've got variable speed on the left, and we've got variable rotation on the right. And of course, today we can do that with pulse width modulation or with an H-bridge circuit. So that's kind of a neat juxtaposition of the old versus the new. All right, this is more of the modern mechanical brain in action. So I'm showing a demonstration of a winch lifting up weights. And let's say you wanted to have the winch lift up the weights at the same speed, regardless of how much weight it's picking up. So if you do it in an open loop, the more weight it picks up, the slower it goes as the engine gets, or as the motor gets bogged down. So what you could do is in a manual mode, you could be the feedback loop, and you could actually give it more gas, more power to the motor as it picks up more weight. So it's slowing down, so I'm giving it more gas. And of course, the ultimate extension of this is having the computer in the loop. So there's a microcontroller chip underneath this magnifying glass, and it's showing feedback from a quadrant encoder, telling it to give it more gas if it's not going fast enough, and the weights all get picked up at the same speed. And so I actually decapped a Propeller 1 chip for this using some nitric acid, and you actually see the silicon of the Propeller 1 chip, which is kind of cool. And Chip, I'm still working on trying to get a Propeller 2 decapped. You mentioned there was a really tiny couple atom thin layer of aluminum, but I'm very carefully trying to polish that away with a Dremel tool,
Yeah,
so I can get a good picture of that.
Unfortunately, it's just a big power grid. It's pretty boring, and it's an extra thick metal layer that covers everything of interest.
Okay, so I'm really meticulously trying to sand it down to get to something cool.
Yeah. Oh, yeah. You could do that.
Yeah.
Hey, question. You know the one, the little sensor where you run your finger up and down the wire. What was the principle?
Yeah, that was just a linear pot.
But what was providing the change in resistance?
I was just sliding the linear slider up and
Oh,
down.
you were moving the wiper around.
Yeah, it's just a linear pot like you'd find on equalizers.
Okay,
and stuff.
it looked to me like you were just pinching a wire and moving your finger up and down it.
No, that would be cool though. I've seen some pressure-based sensors that are kind of like that. Nope, just regular old linear potentiometer. This is the back side of this. Let me just make sure I show that transition again. So we're behind the scenes on here are about I don't know, 8 or 9 Propeller 1 chips. So what we did is we made each one of these little sections kind of its own module, and there's a central chip that deals with the screen and stuff. So there's like almost a dozen microcontrollers, Propeller 1 microcontroller chips behind the scene. So add up all those cogs. So you can see a Propeller Mini there. We've got 2 Propeller Minis on this section. So there's a bunch of propellers, and I had different students take on different parts of these, and each one was controlled by its own propeller chip. And then we just sent out a 4-bit system to tell it what mode to do at any point in time. So kind of cheated and just did a quick parallel interface to a one-way interface so that the master controller can tell it which ones to operate. This is an example of straight line motion mechanism, which is kind of neat. A Poncelet-Lipkin mechanism that takes the rotary motion again from something simple and makes a straight line motion on the output. And Ken mentioned I work for AMF Bowling. That's actually the mechanism on the AMF machines, at least, that pulls, it's actually tilted 90 degrees, and it's what pulls the bowling pins back into the machine so they can be sorted after you've played. So the thing that has that little bumper thing come down and then pull everything back is basically this mechanism running off just an induction motor. So one of the reasons I left AMF was everything there was powered off of 3 induction motors. And they, so it's just ingenious linkages, just like this mechanism wall at work. So that kind of got me in love with mechanisms that sent me to grad school to actually learn more about how to make stuff like this. But then I quickly learned mechatronics is the new way we want to make this stuff. And I've worked on trying to pioneer how to teach that to the students over the last couple of years. So, so yeah, this is the lab where we make that happen. And you can see there's another kind of fun project. They made this cassette tape looking table. It's also a boombox inside of it. It's got speakers. But for the tape part, they used these arrays of the WS2812B addressable RGB LEDs, which is kind of neat. So they've got Propeller 1 chips telling it, which LEDs to light to make different patterns. That's sort of one of the projects they work on, is updating that every couple of months. All right, so that's the mechatronics lab. Any questions about that?
A quick question just about how you teach all this. So you showed a whole bunch of different machines, 3D printers, lasers, routers. I saw a couple CNCs. Do you use one project to use all machines, or do you train them on the individual machines one by one and then have them do their projects? Like how do you introduce all that? Because it's complicated to have so many tools.
Yeah, it's a great question. So the students they declare their major at the end of their first year, and then they're with us for 3 more years. So all of our engineering students have kind of a generic first year program where they do intro to computer science, the calculus courses, but then they don't get specific until their second year. So it's not until their 3rd year spring that they take my survey mechatronics course that all of them have to take. So all mechanical engineers have to take mechatronics at UVA. That's not the same at all universities, but we've really pushed mechatronics at UVA because we kind of see this as the future of mechanical engineering. Whereas in some universities in the US, it's not very common, but especially in Europe and Japan and places, they're just making mechatronics its own major. So you just would major in mechatronics. I believe firmly that it's just an extension of mechanical engineering, that mechanical engineers need to get a little bit more familiar with computer science and electronics to be able to make their machines move in a modern context. But and you kind of need some of the depth you get in mechanical engineering to really bring this stuff to life. But there's different opinions and different flavors of this at different parts of the world. In terms of your question, Ken, in the survey course, I basically get them familiar with electronics, and that's kind of where this book is stemming out of with the Propeller 2 chip. And then it's not until their 4th year when they're working on their capstone design projects. So all of the engineers, is sort of a rite of passage, have to spend at least a semester, usually 2 semesters, building some sort of a neat project. Since that's where things like that robot or the jet ski kayak and stuff would come out of a project like that, where you've got a couple students, with a budget of like $1,000, trying to design something really amazing, and spending a lot of time doing it. And that's sort of an experience too. So I've learned that to be a good teacher, it's not so much about the end product, it's more about the process. So my job as sort of their coach through those projects is to make sure I'm setting the bar high enough that they're really going to grow and stretch themselves to get there. But I also can't make it so easy that they just get there and it wasn't a challenge, they haven't really done anything. So it's always tricky to make the bar just high enough that they have a chance to get over it, but also, because of calling things so close, they don't always quite get finished with everything. They always underestimate how long things are going to take in terms of design. And I think that's just human nature, but it's good to get that out of their system before they go off and work for a company and have financial implications when they don't get their projects done on time. So, and then, so in the capstone course, I have some projects for teaching 3D printing that I like, where I have them build, it's kind of the modern version of a spaghetti bridge project. So they build cantilever bridges with 3D printing, and they try to hold as much weight as possible cantilevered out from where they're mounted onto a post. And and it's a contest. So it's like this spaghetti bridge, whoever holds the most weight wins. But there's a second aspect of that contest, and that kind of brings up what is engineering in a nutshell, and that is predicting the future using math models. So we teach them how to do finite element analysis. They've got to design their parts in computer-aided design beforehand. And then they have the computer break that little shape, whatever they come up with, into thousands of little elements. They program in the material properties of the ABS plastic they're using on the 3D printers. And then it anticipates where the maximum stresses are going to occur, and they can decide at what weight it's going to break. So in a way, they're kind of looking into a crystal ball of mathematics and seeing, okay, well, because I built this bridge out of this material in this particular geometry, I'm predicting it's going to break at exactly 83 pounds or something of weight on it. So so this is the other contest, is who can predict the closest to where it's actually going to break. So whoever can hold the most weight and whoever can create the best prediction of how things are going to, what the future will hold.
So does the science really help predict pretty well, or is it always off a bit?
It does. I've found that because the 3D printing process creates sort of an anisotropic material, because it's layering things, the material is definitely weakest along the little lines that it's putting down as it prints up the part a little bit at a time. So it's not a perfect model. They usually just use an isotropic, the same material properties in all direction model as they're doing the finite element analysis. But it's close enough to kind of show the power of why engineers use math, and that is again to kind of look into a crystal ball to see what the future holds before you take the time and money to do things. So same with the guitars, it's sort of an exercise where they do the finite element analysis in terms of anticipating resonant frequencies, but they it does make the guitars tend to sound better. And then some of the guitars, we made one really fancy one that's shaped like the UVA rotunda, where we really spent a lot of time analyzing it, and we adjusted the shape until we got a perfect resonance at 440 hertz, a concert A. And after we built it and tuned it all up, we kind of suspended it from a wire and smacked it with a rubber hammer mallet while we had a microphone attached to it. And sure enough, a fundamental frequency was at 440 hertz. So it's kind of cool. That was a much denser mahogany wood, so it was a little bit easier to work with than just pine. I'm an experimentalist. So whenever I see a cool new toy like that, the first thing I do is I've got to try it. I got to believe it. So one of the things I did is I took one of my tricks is I'll take calipers, set them to a known distance, and then take a picture of something. So I did this with aluminum, a cast aluminum tuning fork that had whatever the frequency was stamped on it. And so I took a picture of it with the calipers, traced it in, I think in the day it was Autodesk Inventor I was using, and extruded the exact model. So I had basically the same model as this real life tuning fork I had in my hands, ran the finite element analysis, and poof, the fundamental frequency that came back was exactly what was stamped on it. So to me, that's powerful when you get that close with an approximation. Of course, aluminum is isotropic, and that's very easy to model. Anyway, so yeah, it's a good exercise for the students either way. So that's how I teach 3D printing. And then they do for laser cutting, I give them where they have to build a fidget spinner. So they're going to make their own custom fidget spinner that they keep after the course. They've got to learn how to model that and then put bearings into it and figure out. I think I make them they're not allowed to use glue. So they have to figure out fasteners and learn how to tap threads. And then after those warm-up projects, they're ready to start tackling their real projects for the rest of the year. So Ken, that's how we do the teaching of those. And the CNC
Perfect.
routing is a bit more complicated. So for that, it's the advanced mechatronics course where they're building the guitars, and I kind of help them through that. For those of you that haven't used CNC routers, it's not the same as 3D printing. 3D printing is two-dimensional printing, one layer at a time, that adds up to 3 dimensions. CNC machining, you're literally dealing with 3 dimensions all the time. If you're not careful, you're putting the milling bit in your tool path, you'll hit clamps or you'll cut off a piece you actually wanted to keep. So it's exponentially more difficult to do the computer-aided manufacturing CAM software toolpath generation than it is to do 3D printing, where you just basically bring in an STL and hit print. So, but you can make your stuff out of all different types of materials if you're subtractively using milling machines. We do have another facility. I don't have any videos now for it, but it is another sort of experiential learning center, a makerspace for the engineering school. That's where the water jet is housed, and that has literally millions of dollars of equipment. A YCM milling machine that's easily $250,000 that has an extra axis that can kind of tilt the part as you're cutting it. They've got a Haas lathe, the most beautiful, Miller Dynasty TIG welders you can imagine. And so just all kinds of cool toys for the students to play with. So those are some of the perks of being within academia at a semi-large university like UVA. There's a lot of money coming in from research and donors and stuff that lets us get all kinds of cool toys. All right, so this is one of the reasons why I've moved on to the Propeller 2-chip, because it's, to me, the kind of most awesome microcontroller toy I can get my hands on. And so what I did last year around January, unfortunately due to the pandemic, I wasn't able to teach my normal lab course to, I think I had 86 students last year in person, because none of us were vaccinated at that point. And so what I did instead was I made a kit, and I actually made, I'll bring this up large. I actually made about 100 of these kits. And so I made them really nice, spared no expense, made them out of wood, made them look kind of steampunk retro. And because of that, I think the students tend to respect them a little bit more and not trash them. I made them modular so we can attach things like wheels and stuff later on, or different components, sensors and stuff to these little threaded T-nut inserts that I put on the back. And I used a really large breadboard because I found mechanical engineers aren't really used to electronics. We need to spread things out. Otherwise, we're not careful about letting metal touch metal, and that's not good. The other thing that really helps us out in terms of conceptualization is an amp meter. So a visual analog amp meter easily lets the students see instantly when they've short-circuited something and this meter and this spikes. And so I'm hoping to recreate some of this stuff, not all of it, for the kit that we're building with Parallax. I'm not sure if we'll be able to keep the amp meter, but or this variable power supply was kind of nice, but I've had some problems with it. So I tried to go really cheap and use everything runs off of 5 volts on this thing. I've got fuses, big fuses that are easy to replace, and students do blow these up occasionally. And I've got the 5 volts going into a boost converter, which boosts it up to about 12 volts. And that allows them to use a buck converter on this side, which has a nice display. And that's coupled to this extra potentiometer that makes it very easy to adjust the voltage coming out of the power supply. And that goes into this strip of the breadboard under here. So it's a really convenient power supply, with the exception of the fact that you can't start up under load. So for some reason, the way these things start up, if they've got any load on them, they'll kind of freak out and go to an avalanche current condition where they freak out and this spikes and pretty soon a fuse will blow. So again, I'm not sure if it's going to be worth putting this into our kit, but it's been working pretty well on these. And then we break out, of course, some of the pins from the P2 chip. The P2 edge chip is the star of the show, of course, and because it's an edge, it just pops in and out, which is really nice. And just because this thing is such a kind of race car Ferrari, I threw a Ferrari red heatsink on the back. It doesn't really need that. I just thought that was kind of cool. And yeah, so any questions about that? Actually, it occurs to me I've got another camera I could switch to that might make this a little easier. So any questions about some of the features on this? I threw little extra fuses in that just kind of helps to space things out. I don't think we need that. At this point, we've had the total of about maybe 150, 160 students use these. My course is only halfway through right now, but we have not blown out a single pin on these Propeller 2 chips, which I think is phenomenal testament to how great the engineering was on making these smart pins and just, you know, how meticulously this chip was made. So I've had discussions with Chip before, and he said that these could probably drive us short for a couple minutes, and we've proven that. We've definitely done some horrible things to these and not had any problems. The only problem I've had was once during stress testing where I was really just trying to figure out every possible way I could hurt these things, and I was able to somehow blow out one of these tiny little 3.3 volt regulators. But other than that, you know, they've all just been through the ringer and back with no scars, which is awesome. So I have utmost confidence in this platform, and you know, I'm definitely a firm believer in it from here on out. All right, I threw a bar graph LED over here just for fun. We use that in one of the experiments. It helps to understand binary. Another thing I found that's useful that we're going to add to the kits is I've got a 3.3 volt regulator on the separate little, I've got one here. It's a separate little board you can get super cheap. So it's just a linear regulator, but it's just so easy to plug on here. It even has a nice little light to let you know if it's working. And I've also put little LEDs in here to show them if they blow up with power supply. So if they lose, say, their 3.3 volt supply, then this will go off and they'll know. These are kind of cool. They're LEDs with little resistors built inside of the LEDs. They're optimized for 12 volts, but it's kind of neat to not have to use current limiting resistors with the LEDs. But I've decided that would get too confusing to use throughout the course because people would, you know, take the course and then go out and get any old LED and just blow it up instantly by not putting a current limiting resistor in it. All right, so are there any questions about this platform? Are you interested in how I've made it? I showed a little bit of this before, but I'm happy to show it again if people are interested.
Seems no questions. And you might want to point out the one we hope to have will be a square box that we laser cut the bottom of.
Yes, so there are advantages of making things out of wood. I'll switch over to the other video. The major advantage, at least up until recently, is it's pretty cheap. It grows on trees. But another major advantage I found in here is that it's nice and insulative, whereas another platform I've worked on for many years where they all shared stations in the lab was made out of aluminum, and obviously whenever something touched that wasn't supposed to and that was grounded, that was bad. So so that's another benefit, is having a nice insulative thing. But the other major benefit is we can just throw these in the laser cutter and cut out the hole patterns, and that's how I made these original boxes. But this was fairly time intensive, and I did have some help on making the boxes in some parts with a carpenter we have in our department. So my idea is to come up with a really simple way to make a kit and have people assemble the kit as part of what we're creating with Parallax. So the idea is, my breakthrough last summer when I was digging into this was I found these little art boxes that are pre-made that are meant for painting on and then hanging on walls and stuff. And they can be laser cut very easily, and they're pretty inexpensive. So the idea is this could be the platform that everything's built upon. People could get these and then decide if they want to stain them or sand them or paint them or do whatever they want. And if it's a class, of 100 students, everybody could have a contest to see who makes the coolest looking customization of theirs before they assemble everything. So I'm still working on the details of exactly how we're going to do that. And I can talk more about kind of where we are in the book too at some point. Do you want to do that now, Ken, or save that for later?
Your choice.
I'll walk you through kind of real quick a video of making these last year in January and February. I just went all out and spent about a month, and as many hours fit into a month almost to make these things happen. So I designed them all in CAD. I'm using a laser cutter to cut out the bases of them, laser cutters to cut out an acrylic top that goes over them. These are making, soldering together the pins on the regulators. So basically trying to mass produce a bunch of these. Having the 3D printers helps, so particularly a whole fleet of these that can just take parts like the 3D printed parts that hold down these breadboards arrays. I wanted to be able to replace these very easily. So that's why I went through the extra expense to be able to make these and push them down, or to make these little holders for the amp meters. And this actually has a nice feature where the little screwdriver for adjusting trim pots is built into the back of it. So you just pull out the trim pot adjuster screwdriver. Because it's 3D printed, you can make it any shape you want. So that's what I did. And so it just gives you an idea of kind of the mass production aspect of this. Of course, when you have a 3D printer, you just hit print, but the things like soldering and assembly took a while, staining, painting, soldering. So here I'm just tinning stranded wires. So lots of work. So anyway, so I've learned a lot in doing this, and the cool thing is these have proved to be very robust. This year, the students are actually carrying them around in a little tote bag all over the campus, and they're holding up really well. So I'm pleased with this platform.
Yep, I did. It definitely looks fixed. Whatever you did,
Okay.
it's much better now.
So anyways, that's the gist of how we made these. So now on to Ken, what Ken was alluding to is that we're trying to figure out how to make these, and the plan was to make them last fall while I was on a sabbatical leave, and I'd really spent about a month, late summer, early fall, working out a final bill of material to get everything made and hopefully have Parallax be able to sell the kit for $300, which is not an easy task. So I was trying to get the most bang for the buck out of every component I could get. So I bought like 5 of every type of sensor and stuff that I could find, trying to vet which ones were the best. Things like H bridges, like this chip here is a pretty inexpensive H bridge that works well. It's a dual H bridge. And then the whole sort of electronics economy exploded, and everything just went crazy. And obviously there were microchip shortages, which you've heard of, but also just all imports from Shenzhen, and everything just went nuts. And so that kind of threw everything out the window for a while. So we're kind of waiting for the dust to settle before we kind of invest in the final bill of materials and how this is all going to work. But I can kind of give you a hint as to some of the things I've looked at on this. Let me see if I can pull up a. So our goal is to try to get something out this summer. Finally, that's the hope. So here's just a quick example of some of the things I've vetted and worked through to throw into a kit. And if anybody has ideas for other things they'd like to see in it, that would be great too. So obviously the P2 Edge module is going to be the star of the show, and some kind of a breakout board for that, and the programmer plug. So this makes sense. In terms of how much of this we can actually recreate and still keep within budget, we got to do some experimentation. But this is basically everything I was going to throw into this, if possible. I'm sorry, I'm vetting a bunch of parts too. That's why there's multiples of it. So definitely a potentiometer. Still kind of working out all the different sensors that we can fit into it. And definitely some kind of a motor and a DC brush motor. And I've looked into the ones that you can get that have the quadrant encoders built into them. So this would be ideal, but they cost about $15 or so. What I've been using in my course are these little yellow plastic gear motors, and they are the absolute cheapest motor you could possibly imagine. But with some Mechatronics, we're actually able to get them to work pretty well. So I have the students right now for Friday working on building a servo system out of these little cheap gearhead motors, where they've got a homemade quadrant encoder system that basically, and then a proportional controller that lets them work pretty well. And then of course we'll cover RC servo motors and stepper motors. And for the stepper motors, I'm just trying to get, there's a hard to find, but they have 6 lead ones that can actually be powered as unipolar or bipolar stepper motors. So I think it's very useful to start by learning how a stepper motor works in unipolar mode, so that you can get to visualize kind of how it's stepping through its phases before you jump into the current going both ways in a 4-wire bipolar stepper motor. So hopefully we'll be able to get something cool for that. And yeah, just some other components like transistors and resistors, of course, to try to teach the basics of how mechatronics works. Right, so any questions? This isn't final. I just want to give you an idea of kind of where we're going. It's probably what you'd expect. Or requests for things that people really think should be in a mechatronics kind of learning kit.
So Gavin, are you doing anything with sound?
Yeah, that's a great question. So I have headphone adapters, and I think we can probably guess that most people would have headphones or powered speakers at home they could plug into this. I'm just starting to mess around with the digital analog converters, and I've got a lab that's coming up in 2 weeks that I'm going to recreate or kind of create from scratch based off another lab I'd made for the P2 2 years ago, which is going to use it's going to show sampling rates, Nyquist frequency, Nyquist criterion, and I'm basically going to be creating with smart pins a digital to analog output to create like a sine wave, for example. And then I've been playing around with actually making from scratch a successive approximation analog digital converter, just an 8-bit one that runs off of the DAC and a comparator built into one of the smart pins, so they can kind of understand how that sort of ADC works. And the idea is they'd have a fixed sampling rate, and they're going to be sampling in a sine wave and then seeing the aliasing effects that happen if they go past the Nyquist frequency. So I think it would be building upon that to try to make tones and sounds and stuff. I saw on the forums that somebody worked out a really neat retro, was it a game, the Amigo or something? And Ken, you did a demo of this? That seemed really cool. I've got a student that was asking to do something with sound for extra credit, so I think I'm gonna send him over to that post and that code and see if you can get something cool working with that.
Kevin, we were thinking for a while, the DACs can do actually pretty good hi-fi quality signaling. If you were to gang like 4 pins together in the 3.3 volt, 124 ohm mode, that'd be like what, 62, 31 ohms impedance, right? Which, and you can get headphones that are 31 ohms. I think some are 16 ohms, but 8 ohms is typically too low for headphones. They don't come that way. But real good hi-fi headphones are typically about 32 ohms. So with 4 pins, you could drive one of those channels, but you have this problem of you have a common on the headphone jack. You have ground, and then you have 2 signals. So you can't do, if you could do differential signaling, you could have a lot of freedom, but because you have this common that you can't, modulate across 2 channels, maybe there's a way to do that, but what we figured would work is to take 4 pins, gang them in the low impedance DAC mode per left and per right, and then use a high quality film capacitor, like maybe 1 microfarad, which is kind of typically a big $3 part, but that's important for the higher frequencies. And then for the
that's just to decouple the offset?
Yeah. So you have a common ground, so that your headphones will connect to ground. So you have to have an AC signal going to the transducer. So
I normally go the opposite route, and I've got these really cheap, like almost dollar store speakers that I have the students just do horrible things with, and they'll just plug things in, even though they're definitely not impedance matched, and it seems to be okay. But
yeah,
it
would work.
But it definitely not audiophile sound coming out. But that's what we've been using with the P1s to do the talk commands and stuff. But yeah, I'd really love to work with you this summer to try to come up with some neat ways to add some high quality sound into this. Of course, sound is kind of tangential to mechatronics that I'm trying to
Right.
cover, but it's definitely something we should be doing. I was looking into the different ADC scope modes and how you had some ones that were 30 times zoom and stuff onto the voltage that seems like that's meant for this kind of audio processing
Yeah,
stuff.
for AC signals, because you're apart from ground them. But if you're AC coupled, you can measure stuff. But anyway, use a 1 microfarad, good quality film cap, maybe a 2 microfarad. They're largest devices, they're wrapped.
Mhm,
And then
yep.
for the base, get like 1,000 microfarad electrolytic, because that's less critical. And you just run those 2 devices in parallel. So it's really 2 caps per channel, and you could have maybe like audiophile quality stuff. And I really want to I bought a little DAC for my stereo here for like 99 bucks. I said it was pretty good. It actually is really good. And I stream Amazon Music now, but I'd like to be able just to take that. I run a coax to it from my computer. So it's an SPDIF stream. It'd be cool to just make a little decoder. And I want to try just running the P2 chip with those caps and seeing if it's at all competitive with this super fancy DAC, which is a good deal at 99 bucks. I mean,
That would be amazing. Yeah. But so you've got an 8-bit DAC and then dithering to get around 16 bits, right? With the smart pin.
Yeah. Yeah. And you can in software change things up to dither even another 4 bits within the period of an audio sample.
Wow. Okay, cool. Yeah, this is going to be great to show off these capabilities. Yeah, I'm excited. We need you to create another speech synthesis object for us so we can use this with the P2.
Yeah, good idea.
Oh, you know what? Okay, one thing I've always wanted to do is to do spatiality this way. It's just time delay and then level difference, right? So you model the head as like, maybe it sounds over here, you're going to hit this ear. This ear is like 1.5 milliseconds later. But this is real tricky. This is called azimuth, I think. And it's the pinnae in your ears. These ridges form like notch filters and resonators that help you see how it's kind of a logarithmic curve. That is what tells you if the sound is above you or below you.
Wow.
So, but we could do that with some filtering algorithms, because then you could take a sound, like you could take a monaural sound source and completely spatially space it in 3D psychoacoustically.
Cool. Yeah. I can see that this actually having real applications in the virtual reality world as people are starting to wear the goggles let them see in 3 dimensions, but they're still just plugging headphones in. If they actually had more 3-dimensional headphones, but then more importantly, a thing that can process that based on whatever data the graphics cards are spitting out to know kind of where the sound should be coming from in games and stuff, that'd be kind of cool.
So Gavin, interrupt with 2 questions about the hardware you're showing. Were the kits funded by a grant or normal department budget?
This was a grant.
Okay. And how about all the equipment you buy though? That's kind of department budget or grant as well.
Yeah. So for the for the capstones, it's typically, like I said, around $1,000 a project. Of course, the students are paying tuition, so some of that gets funneled back into the projects. And at UVA, we're a bit fortunate to have private donors that are fairly generous and are able to allow a lot of our extracurricular clubs and stuff to be sponsored by these gifts. I know other universities that are kind of our peer institutions are more they go out in industry and get industry to come in and kind of have a rapport where they're the industry is giving money for equipment, but then there's they get first dibs on the students for hiring and stuff. So
okay, and then I know you use a ton of sensors, but what sensors do you want to include in the kit? I saw the Malexis Hall effect is one.
Sure. So all this we need to work with. So the ones I know for sure.
Maybe your favorites, the absolute must-haves, and you can go through that quickly.
This has been pretty cool. And they've got all different flavors of these, but they basically have a little tiny comparator integrated circuit chip on these. And you've got ones for measuring soil moisture, ones with photoresistors on them. So they just come pre-done, and you've got a potentiometer that you adjust the threshold voltage for the comparator. In this case, it's an IR emitter and the clear LED, and then it comes back to the photodiode, the darker one. And so this is, I use these a lot. These are on our systems with the motors. I've got acrylic discs that are very simple to laser cut to kind of teach the students how encoders would work. And I can demonstrate this later, but this is an example of a laser cut mirrored disc. And then this can measure where the spokes are as this rotates over it. And again, I'll show you that in action in a minute.
Okay,
Hey,
and for
you
those
could
who
do
are,
some time of flight stuff with that, couldn't you?
I don't think you have control over.
that's like
no,
a
you can't.
$1 cheapie that he's got there.
Yeah, this is literally $1.29 right now on Amazon. So
Oh,
it's kind of cool.
that has the decoder and the whole protocol and everything in it, right?
No, but the P2 chip does, thanks to the smart pin. So we actually use
Okay.
2 of these to do a quadrature encoder with these are offset on the same acrylic disc, and one of the smart pins decodes the quadrature no problem, and it turns this into a servo motor, which is remarkable. And again, the students are working on that right now in my class. So I like these sensors, and I'm trying to think of new novel things I've been experimenting with. The a Hall effect sensor might be nice. It's not necessary. The Melexis ones you guys, or Melexis ones are really nice, that Parallax carries. There you can also, without the comparator, just get these other optical IR sensors. And these, they basically just have a fancy piece of plastic around them. But if you pop the plastic off, they're just an LED and a photo diode.
And for any teachers who are hanging out, Gavin, we should point out that you can usually get a box of these really low cost sensors on Amazon for $50.
Yeah, so it's kind of neat the way
Which is
that
helpful to have in class.
yeah, so and so a lot of these things have become kind of standard and they're pretty easy to find. But yeah, again, we'll have to discuss kind of other ones we can fit in. And you know, I love parallax sensors like the ping sensor and stuff too.
What other type
Yes.
of thing would you use in mechatronics?
So the definition of a mechatronic system is a sensor feeding data to a microcontroller, which is then moving actuators. So those 3 things usually come together in most mechatronic systems. So sensors are fundamental to any mechatronic system. People then say, well, what about stepper motors? Those are open loop most of the time. So, you know, how is there a sensor in there? But usually you have to home them against a limit switch, which counts as a sensor. So that's still got all 3. So really any sensor, Stephen, could be used in mechatronics. You know, it's just something to give the controller some idea of what's happening in the outside world before it starts moving things. I've also got a temperature sensor in my current kit that I give the students. So I give them this little tin full of kits, and it's and so that just outputs an analog voltage that's calibrated to be degrees Fahrenheit or Celsius. So if you get like 0.73 volts, it means it's 73 degrees.
Hey, Gavin.
Yeah.
What if you could make something that would like, you know, have you ever seen those toys that are like propellers with like shafts and you go like this, and you let go,
Yep.
they spin and fly?
Yeah.
Could you make something that's like magnetically spun and levitated? And
Cool.
but it has a mechanical aspect where when the centrifugal force gets high enough, it goes from flat to like this. So it takes off at some point. Like imagine you could spin it and then at enough RPM, it would be like a firework.
Yeah. Yeah, I think that's cool. You know, I'm sure I've had students that have tried to build quadcopters with Propeller 2, and you guys had one that had a Propeller 2 running, right? Propeller 1 running it. So yeah, I think the Propeller 2 is more than capable for doing stuff like that.
So Gavin, do you want to show some of the curriculum now? The book
Yeah,
progress?
let's do that. So
otherwise we'll take you in all possible directions.
sure. So let's see.
And any questions in the chat are welcome to.
All right, so I gave an overview last year, and so all the labs have been improved a bit. I guess just in terms of the course overview, I start off with Tinkercad, and I did this again this year. Last year I did it because I was just stalling those. I was making all these kits. But let me just kind of walk you through. For those of you that are educators, particularly in the K through 12 area, Tinkercad is pretty cool. And if you haven't seen it yet, it's definitely worth looking at. So what I do, even though these are students that already are going to get their kits in real life, I start them off in Tinkercad just because it's sort of a safe playground where if they blow something up, nothing bad happens in real life. It doesn't cost me anything. So they even start as basic as just making little lemon batteries to kind of understand voltage and current. And you basically can simulate the stuff in Tinkercad and So you can bring in stuff, you can bring in microbits, you can bring in Arduinos, and then just wire up your prototypes and I lost the link. Okay, somehow this got screwed up, but you basically just prototype your circuits and sorry, I don't know how this got screwed up. I was on another tab. So it threw in Parallax IR sensor. There we go. So this was something I had the students work on where they basically had to simulate a hand wash timer system where they'd have a photodetector or photoresistor detecting light, and they ran some basic Blockly code to make this countdown as somebody in this case was washing their hands. They have a little thing doing soap dispensing with this thing, and that piezo buzzer is not supposed to be in there either. Anyway, so just sort of an example of where you can build your circuits and simulate them without having to spend any money on any real life equipment. So this is a great warm-up tool to kind of walk them through some of this. I think I'm going to take some of these Tinkercad exercises and actually incorporate them into real life for our book. I'm not sure which ones are going to make the cut though. And so then they study how switches work, and that kind of leads them to how computers think and how logic gates work. So they build their logic gates out of transistors through the simulation. They build counters, and then they build a 4-bit adder system where they can add up using one of these chips, which is in Tinkercad, to understand kind of how computers tick, what makes binary numbers add together inside of a processor, and that kind of leads them eventually into how assembly programming works on the Propeller 2 chip. So then they get to the real life stuff, and this is the first lab. I'll actually just show you the Google Docs. So right now, are any questions about Tinkercad before I close this? Again, for you educators, this is run by Autodesk, juggernaut in the engineering software realm, but they give this out for free, so students can use this, and it's just a really great way to get started in this stuff without any cost. All right, so in terms of our kit, we're going to be covering the basics of mechatronics. We're going to obviously be showcasing the Propeller 2 chip. The very first thing we do is sort of the hello world of microcontrollers, which is to link an LED. I think it's always cool to make a stoplight simulation with the red, yellow, and red LED. And so that's what they do. They just they start off by getting pins blinking to blink LEDs and just coming up with the simplest code possible. One of the really nice things about the Propeller 2 chip is that you can turn pins on and off in a really simple way using these pin high and pin low commands. You can also just call them pin H for short. So Chip was really clever about making lots of different ways to kind of do the same thing so that people can kind of go about it in their own unique idiom. And also a new thing in the Spin2 language is just this really nice, easy way to make it wait for a number of milliseconds rather than having to go through and show off how the system clock works right off the bat. So keeping the program really simple, basically in this first exercise, this first chapter, or the first lab of this book, it's mostly just trying to warm everybody up to kind of how electronics works. So we have a multimeter in the kit right now, but I've actually, at this point, now that we've got the keyboard and mouse back and forth between the PC and the debug screens, I really think we can make the multimeter part of this kit. So again, for those of you who are new, this Propeller 2 chip is unique because every one of the 64 IO pins has a smart pin kind of mode where it can do, I think, 32 different crazy things. And one of those things is analog to digital conversion, actually a couple different flavors of that. And so you've got a really good analog digital converter on every one of the 64 pins. So that means every one of these 64 pins can act like a digital multimeter or like an oscilloscope. And that's kind of mind blowing. And all that happens in parallel to the 8 parallel 32-bit processors on this chip. So it's capable. So I'm really hoping to bring out some of the oscilloscope functionality and the multimeter functionality essentially on this chip for our kit. So that'll help to save some money because the kit and the Propeller 2 chip will function like a multimeter. And it'll probably have some extra things like shunt resistors and stuff to work for current mode. And all right, so then they go through some exercises working on how this works, how to measure current, studying potentiometers, and so basic electronics type stuff, how voltage dividers work, and then how mechanical relays work. And what I did was cut the plastic off these mechanical relays, but we found some clear ones that might work just as well. I find that even these mechanical engineers have a rough time wrapping their heads around how mechanical relay functions. And I think just being able to see it like this really helps. But and then at the end, they build a complete mechatronic system. So what I do here is they actually use, this is showing you the discs, the laser cut acrylic discs with the mirrored surface. And it's using that IR distance sensor, which reflects up off the bottom mirrored side and comes back every time a spoke goes by. So the output signal just goes into a propeller input, and it can detect where it hits the spoke. So they basically are trying to build a simple Geneva drive system, like I showed you with those white discs before, where they're trying to get it to move and then stop and then move and then stop as it hits the spoke. So they're trying to turn it into an intermittent motion generation. And because it has a sensor feeding data to the controller, the Propeller 2-chip brain, which then decides how to move, turn on the relay to move the actuator to the motor, this is mechatronics in action. So, so yeah, they bring it all together and they basically make a modern version of a Geneva drive like this. Is the grand finale of that first kind of exercise. All right, and then the second chapter lab is all about the Propeller 2-chip, and we talk about how it works. It's got parallel processors, and we get a little fancier in terms of how to program it. So I teach them how the direction registers work. So not just using pin high and pin low, but actually understanding that if you set the direction bits for the pins, and then you can adjust the output register or how to read the input register. So trying to conceptually walk everybody through that. And oh, another thing is a shout out to Jeff as a thank you. Early this semester, as we were starting this course, he added the version that disables the programming to EEPROM or the flash. And this is actually really important for courses like ours, where the students are just constantly prototyping new circuits and codes at the same time all the time. So they'll finish one circuit and they move on to the next one. If they have got the old code in the flash while they build their new circuits, as soon as they turn on their chip, their power to their board, it starts running that old code, which can then short circuit things on their board. So just always using RAM instead of flash is a huge safety feature that's just saved us a ton of headaches, both in debugging and in the possibilities of shorting out components. So thanks for making that happen. So that's really useful for us. All right, and then they're working in understanding more about how to program and spin. They're learning about how to deal with the input output registers exactly, how to deal with setting up counting and timing in the Propeller 2 architecture, and just teaching them tricks there. I won't go through everything because I've already gone past an hour here. How parallel processing works, how to visualize that, and you know, how to create methods to break up your code, make it more general. And then how PASM 2, so how propeller assembly language works. So again, for those of you that aren't familiar, what Chip has done with Propeller 1 and now Propeller 2 is really made assembly accessible. And in terms of mechatronics, which is quite a bit different from just general computer science. So computer science is kind of a very kind of theoretical take on programming, and it's typically meant for to tackle very complex problems that involve hundreds or thousands of millions of lines of code, whereas in microcontrollers is typically far fewer lines of codes doing much simpler things, where being able to talk directly on the metal to the processor in its language is incredibly robust and worthwhile, even though it's a little bit complicated. So what Chip has created is this complex instruction set architecture for this P2. It's kind of a joy to work with at the assembly level, which you can't say about most chips. So this is showing kind of how the assembly works in terms of how the assembly turns into the ones and zeros and how those are manipulated by the processor. So in this case, it's just this is basically the stoplight program in assembly, where I deliberately made addresses rather than the variables so that people could understand it. So I've actually got 3 different codes that are all identical. So this is normal assembly, the way to write it. This is replacing the line names with actual address numbers instead. And this is the actual operation code.
Neat
machine code.
transition. Yeah, that conveys the whole process, the source code, what the assembler does in 2 steps. And then that's the idea. Is I'm trying to get the students to understand kind of what, or the reader to understand what assembly is and why you'd want to do it, and just being able to understand that you're talking to the computer in the ones and zeros that it understands. And I mentioned this last time a year ago, Chip, but I've actually run this code. So if you run this code on the bottom right, it just works flawlessly, the same as this code, if you're able to work this out the right way. All right, so that's
that's kind of how they get into assembly. Then we talk about external objects, which is another really powerful thing about this environment with Spin 2 is you can just grab other people's objects and call methods from that. So we used Johnny Mac's easy analog a lot and serial. And so for those of you who don't know, Johnny Mac has written a lot of objects to get everybody started. And these came out over a year ago, and they've been super helpful as the students have explored this in my course. But we need more people to help with that. So we need more people on board that are getting the hang of this and willing to help pave the way for other people to follow. And the other thing that really sets this Propeller 2 chip apart is the debug interface when you're using the Propeller tool. And so an extension of that is a really wonderful way to get the students interested in programming, and this is creating video games. And so I gave them this assignment. They actually haven't finished this yet this semester, so I don't have any new games to demo from them this semester, but to kind of whet your appetite. And so maybe Ken, over the summer, I could do another lab forum to just talk about the video games, because I think it almost deserves that.
That'd be super. I'll take that as a commitment.
Yeah, I'm going to try to get a chip hooked up right now and demo this. All right, so I've got this board, and I'm going to hook a joystick module up to it. So just 2 potentiometers, and it has a button feature when you push down on it. So I'm just wiring this up. So this is just this board with this potentiometer hooked up to it. And I'm going to run this code. Not sure it's the right.
Are we supposed to see what you're doing or just your?
Yeah, give me just a second. I had the wrong USB cable plugged in. I've got too many things. The problem with having lots of these boards is I've got like a half a dozen of them on my desk right now. So I had the wrong USB. Forgive me. All right. So this is running off that P2, and this should look familiar to most of you. So this is a debug screen on the Propeller 2, showing the pixels, and this is what you're able to do. To get the students to get excited about programming. So all this is being done on the Propeller 2 chip, and it's I gave them some starter code to get them going, but they basically need to come up with any game they want, and I've given them all kinds of sprites to work with to make this more fun for them. And so all they have to do is load in the data for whatever sprites they want to play with, and they've got all of these to choose from. And so what Chip has done is over the summer made it so that you could bring in these sprite definitions into the Propeller 2 and do things like rotate them and change their transparency. And so all of these different pictures can be manipulated in video games. And obviously the students just go wild over how creative they can get with all their favorite characters and come up with their own themes and storylines and stuff for how these work. All right, so any questions on kind of how that works in general? They're basically just taking these pictures and moving around on coordinates on the screen, and then you're doing things like checking for collisions between the various shapes to figure out how to make whatever they want. To make it fun, we give them some of the teachers they have to deal with on a regular basis, including ones like me. So they have fun, come up with clever ways for me to be tortured and stuff in their games. All the normal characters are in here. All right, and so what I did with a student employee of mine who's also a computer science minor was we worked out a way to convert very easily with an executable any sprite pictures, any PNGs into the format we need for. So this is a little executable, and eventually, again, I'd like to try to work to get this maybe put on a website through Parallax or something, because right now it's not a certified Windows executable, so people might worry about it having a virus or something. But this, you basically just copy and paste this data into a data section of your code, and it's got everything you need to to define a sprite. So what I just did was I converted a picture, in this case of Boba Fett. So it's this picture. And basically the way this is defined is it's every one of these is a pixel, and every pixel references a color palette, and every color palette has a long, and the most significant byte is the alpha channel. So that's the transparency. So this is totally transparent and this is fully opaque. And then you've got the red is a byte and the green and the blue is a byte. So it's 24-bit color. And each of these hex numbers is the index that this pixel would reference. So this one 04 happens to go down and look for the 04 color to put in that pixel. So that's how this works. And then in the game, it to simplify it, I created another objects that it would call, so they wouldn't have to mess up their code with all these lines of just data. But basically these would be the sprite definitions that they'd call in their code. So I just made the Boba Fett one, and I would just come in and throw that down the bottom, and they just load that in. So you just copy and paste it out of our executable, and that way they can make custom pictures. So they don't even have to use the ones in that book, and they just load them in to their game, and then they can just move them around by setting their sprites to various positions.
I should
Which can
probably
vary.
add a good little sprite example into the doc, because I just went and looked at the Spin2 documentation, and it really only gives like the sprite def and the sprite command definitions and doesn't say anything else about it. I think the information is there, but it would be helpful to have a little, well, that's what that debug plot sprites file's for, but just feels
Yeah, I think
underdocumented.
we definitely need more examples. This book will kind of help with that. I'm trying to to
Yeah,
pave the way, but you've given us the infrastructure. Now it's just a question of people coming in and really kind of showing off how to do the cool stuff with it. But again, over the summer I've got a little more bandwidth, Ken. I might pour some more energy into just making this the video game aspect of this a lot easier to duplicate,
have
because
you,
I think there's really something there. There's a lot of people that get excited by these sort of retro style games, particularly the generation right now that's going through high school and college. I think there's a real push to kind of go back to these old NES, Nintendo Entertainment System type games.
yeah,
So it's fun.
have you used the keyboard and the PC key and PC mouse thing much?
Yeah, so this just came out for us last week, and again, thank you to Jeff for working
Oh,
to
yeah.
get this out. So we I haven't used it in Peanut really. I just kind of made sure it kind of worked, but I'm really digging into it now. It's on the Propeller tool, and I'm gonna have my students downloading the new version for using in their labs for next week. The next week they're doing RC servos, but I'm gonna have them type in their positions they want to go to. So I'm kind of working on the interface of how to make that a little bit easier, where it's kind of waiting for keys and figuring out what value it is. And stuff like that. So yeah, I've got high hopes for that. I caught the end of the video for last week's, just so everybody knows, I really wanted to be at these live forums throughout this semester, but I teach a course from 3:30 to 5 on Wednesdays this semester. So I haven't been able to make it. I'm actually been playing hooky for my course today. So I've got the students working on building their guitars today. So, but I haven't been able to make these things live, but it's not because I wasn't interested. It's just I had a course conflict. I think what you're doing with the single step debugger is really cool. And I think it's kind of, I want to create stuff like that, where you've got like a mouse and little virtual buttons you're clicking on to be able to do things. I think having some oscilloscope functionality like that would really be big. And for same with the digital multimeter, where you just kind of click to switch to different modes. So I think that's going to be the start of something really cool in terms of what we can do with this chip. And again, Johnny Mac did some special lectures, tutorials for us on the Nextion displays. And those are cool if you have to embed something somewhere, but most of the times when students are just learning, they're using PCs. And so they've got their Propeller tool open while they're working on it. So being able to debug and stuff with these human machine interfaces is a really neat thing that sets this Propeller 2 apart.
hey, Gavin, can you visualize, you don't have to talk much about it, but I'm just wondering, if the tools were on the chip and the chip could talk to a monitor, keyboard, mouse, would that at all provide, I know it's a little bit of a problem because you need to have separate than their PC to talk to it, but do you have any idea, like the feel of something like that? Would it be an improvement? Because it would tighten the loop up to like zero time for compile and execute. And
I understand what you're getting at, and we've discussed this before, and I think it's cool. The trick is that I think in this day and age, most students don't even have a keyboard and mouse. Everything's just on a laptop, and that's all they have.
Yeah.
So the one exception there is at this point, pretty much everybody has a phone. So if you had some way to be able to use Android and Apple and have it be able to just have an app that you could maybe use, might be another way to go about it. But I understand that would also have the latency and all the weirdness. I think the trick is that you'd have to have some way to interface it. But maybe that interface is a touch screen that attaches rather than having a separate keyboard and a separate mouse and a separate monitor.
Yep.
So the thing you need to keep in mind, though, is that some interesting examples. There's like the Latte Pandas, and you can buy a pretty kind of amazingly competent Windows PC for $150 these days that comes with Windows. So to get to that price point where, you know, it's kind of cool you're doing everything that's kind of acting like a PC, but if you can also just buy the PC for around the same cost, it's just more of a novelty.
Right.
But I've mentioned I got started on programming on a TI calculator and programming in BASIC and in assembly on it back in grade school when I could, you know, sit in math class and pretend like I was working, but I was making games like Tetris and stuff and Snood on these. So it's kind of, you know, I understand having the whole package where you just sit there and you can program on it and it's all self-contained is kind of a neat idea. And I forgot to mention too, another improvement on these this year is I put a USB battery pack on the back. So this is all running off of USB power. So now, especially when we're still kind of at the tail end of this pandemic, all the students are doing their labs in person, but they can go outside around a picnic blanket and just sit outside in the sun, you know, working on their labs. We've always joked in my class about having lab outside in the old days, but now we actually can. It's trivial. You just go outside and sit around on a picnic blanket and do your labs. Everything is self-contained. They've got their laptops hooked up to these battery powered experiment boards. All right, any questions about the video game before I move on?
Lots of interest in the chat from other teachers, so that's positive. I mean, that can be done with minimal hardware too. So I like that for them.
Yeah,
but
again,
I suggested when the book is out in some draft form with these code examples, we'll have them take a look and they could try these and see if they'd want to use that. Because I could see this being used in high school at that level. And we have a number of teachers that want to have this kind of mechatronics or pieces of it in their high school course too.
Yeah, so for those of you out there that are teaching high school, I would say that there's a lot of misconception about how to teach programming from my perspective. And so at the high school level, I don't think you need to be too language specific. I think at this point, students just need to get the hang of how to understand how to, you know, think like a programmer. And I think things like Blockly are perfect for that, at least for getting started. And I think Spin 2 is an excellent language for programming, and it's meant for programming microcontrollers, which the normal go-to languages aren't meant to do. They've got their own specific things. And in fact, almost by definition, the real programming languages like, you know, Python and C are by definition hardware agnostic, where they're not supposed to know anything about the hardware as you're writing the program. That's all supposed to be done by the compilers or the interpreters. So this language and this chip are meant to pair together in a way that makes it a very powerful combination, very efficient combination. And in my opinion, a very intuitive combination. So the way you think about how to program the chip, once you wrap your head around how it works, it just becomes very simple to be able to see exactly what happens. Whereas in a lot of other programming environments, you write a program and then something doesn't work and you really have no idea what didn't make it work. And then you just keep banging your head on it until it actually works. And like, oh, wow, I made the Arduino gods happy or something. And it's a frustrating way to have to go about trying to solve problems or build things when you don't have full agency over them.
Gavin,
so I've just put up the chat. Sorry, I've been behind these. I'm looking at Sherry's comment. So Spin is a high level language that gets interpreted into assembly, and that's something that Chip has just become a master at, is being able to build these assembly interpreters for interpreted languages. And because he designed this chip from scratch, it's got a beautiful interpreter. It's actually very fast and very robust. And the other cool thing is he's added inline assembly to this Spin 2 language. So if you want to be running your Spin code, which is again just kind of like the C you'd see in Arduinos and stuff, it's a very high level, easy to use language. And then when you want to pull out the stops and just have it run at a blazing 6 nanoseconds per instruction, you just jump into a couple assembly codes and then jump back into your spin. So it's really easy to go back and forth. Whereas one example I do with my students to help them understand, compiler in a conceptually is I take the UVA theme song that they all sing at the football games, and I copy those verses into Google Translate online, and I translate it into some other language like French, and then they see it in French. Then I take that, copy and paste the French back into the Google Translator and have it translated back to English, and they see that it's not their same song anymore. That's changed, it's screwed things up. And so that's kind of what a compiler does, is you're writing your high level stuff and you're telling it what to tell the computer, but you've got that middleman there. And that's kind of where things like blue screens come from, is things can get mixed up and misinterpreted. And so just having the power to really dig down and make things as robust as you need them to be is a beautiful aspect of this chip. So, and again, in a lot of the code that students will be writing or we write in mechatronics, you're doing something really simple that doesn't really need to be high level. So let's say you were designing an airbag system for a car. You just want to say, okay, did the accelerometer say that we're decelerating way too quickly? Yes. Okay, deploy the airbag. It's not like, oh, well, I'm just actually going to run a couple hundred lines of bloated software that got compiled down that might have some bugs in it or might not be as efficient as possible. And all of a sudden, while the car's crashing, you get a blue screen when you needed the airbag to come out. So I think there's a logic to looking at microcontroller programming a bit differently than just pure computer science programming, in terms of both the applications, what you're going to do with it, and the depth to which you need to program it or to understand it as you program it.
C
So
is very hardware agnostic, and I've heard that the ARM multi-core chips, I don't know much about it, but I've heard they use like FIFOs to communicate between processors, which I understand that will work. But that's a very dissociated way to go about things. You're marrying two black box systems through FIFOs.
Yeah, I think what you've done here is beautiful, and it's really once you start to understand how it all works, it's a lot of fun to kind of play with, because again, you don't have it's not as frustrating when things don't work to be able to, because it's all out there. It's not that hard to dig down through the levels and to see what's happening.
Gavin, to summarize the book, would you say we have about 6 labs or 4 labs and somewhere around 100 pages of content at the time?
I'd say it's probably more like 150. I'm still tweaking everything this semester. So the other things I've got going on for the rest of the semester are, let me pull up the other ones that are pretty close to finalized. And also should shout out to Stephen, who's been helping me to look over these drafts over the last couple of weeks. So thank you, Stephen. This is lab 3, covering analog digital stuff, kind of juxtaposing analog and digital signals, going into how op amps work, how to use those as comparators and as voltage amplifiers. And also this is kind of a neat thing. You can use the smart pins as oscilloscopes. That's something I've added this year, is really digging into more of how to use your oscilloscope functionality chip. And so this is actually a Propeller chip and the Propeller tool reading the analog signals going into the operational amplifier. In this case, is a voltage amplifier. So the yellow signal is going in and it's amplifying it and increasing the voltage for the green signal that's following it. So this is just awesome that this little Propeller 2 chip can actually be an oscilloscope, because as most of you science teachers know, those usually cost a couple $1,000s. We go into how bipolar junction transistors work and MOSFETs in this lab, and that of course leads into kind of how logic gates work, and then we get into switch debouncing and how that would work. So again, thanks to Stephen for helping me out with the edits on these drafts as they come off the assembly line this semester. Lab 4, we've already done in this course. This is pulse width modulation and motor control. Again, the smart pins are kind of cool that they can create pulse width modulation just by setting up smart pins. So again, every one of these smart pins, for those of you that aren't familiar with this chip, I like to think of it as like a separate little parallel processor. So this chip has 8 parallel, very powerful processors that are running very quickly and have a very rich assembly language. And then you also have these 64 smart pins where each one of these has its own little tiny baby processor that's basically programmed with just 4 lines, the configuration register, and then an X and a Y and a Z register, and you can get it to do all different kinds of fancy things, including generate pulse width modulation signals without any intervention from the main processor. So once you set this thing up, it just generates PWM, and you can generate 64 simultaneous PWM signals if you wanted to, each doing their own separate thing. Same with analog digital conversion, digital analog conversion. Every one of these pins can switch in any of those modes. You can do USB modes. You can do just, yeah, it's really cool what you can do with these. So what I've tried to do is an extension of, I know John Titus has worked a lot on trying to help explain what these smart pins do. So I'm trying to pick some of the ones that are really useful for mechatronics, like the sawtooth PWM generation, and really try to walk people through exactly how that works, because I think it's so powerful once they understand how to make these things tick. Any questions on that?
Actually, the only question I have is this book, will this be available for sale or something, or is this only part of your
I
course?
plan to make it available for sale just so that I can kind of justify to my employers that this has been worthwhile, but it's not really for sale. It's going to be available hopefully on at least a website, or as a download from Parallax. But the idea is you'd be getting a kit as part of it too. But I'm trying to get out of it is just trying to get the word out there. This is kind of a neat chip that people should start paying attention to, and it's perfect for mechatronics. So as long as I get some credit, that's all I need. So just as long as you're not copying and pasting and putting your name on it, I'll give it to you for free.
Hey, Gavin,
Okay.
do you make any
Yeah.
video? Oh, sorry.
Make
I was
any,
gonna ask- I was going to ask, do you make any videos of your teaching? Because that would tie a lot of things together. Like, do you record when you teach your class?
yes, so I'm recording when I teach my class. I'm not too proud of the ones this year because I've had a mask on for most of it, so it's kind of weird. But I think it'd be worth it, especially if we had a website of this. You know, it's easy to put little moving animations and stuff into a website where you can't really do that on a PDF. So I
Right.
like that about the Google Docs. But yeah, it might be interesting to come up with a YouTube channel that kind of helps to explain this stuff as we go. As we go through it.
Stephanie at Parallax mentioned the other day to me in an email that Google Docs is going to have some kind of pageless mode, which is a big deal because, these days I don't even print anything. My HP printer wanted new ink, and in order to scan a document, and I gave it new ink, then it said it needed a new print system. So the whole thing went to the dump. So I have these monitors now, and I just look at everything on screens, and having this old page issue, you tend to want to put page breaks in to position things on the pages. It's kind of an antiquated thing, but there will be some new pageless mode in Google Docs, which is kind of a boon to the whole online documentation thing.
Interesting, yeah. So Google Docs is very interesting the way we can kind of collaborate, and you've done a great job of showing that off with the manuals that you've been working on, where people can suggest comments and changes. And I've done that with these labs too. So I haven't done as much this year just because there's so many weird quirks, like where somebody actually hits a typo and then it sends you an email. But I've used that last year, and I fixed all kinds of typos on the fly with it by having 86 students look over it.
Gavin,
so yeah, so
briefly, I have to step out. Sorry to interrupt. So I'm passing host to Chip. I just want to say this is awesome. And when you're done, Stephen will share something, but be sure to open up for questions as well.
Got it. Thanks. So I'll wrap this
Thank
up
you.
pretty soon, but it's great to see you, Ken.
No real
Thanks.
rush. Thank you.
All right, so yeah, they're generating pulse width modulation. I showed them how to use a low pass filter to be able to filter out the carrier frequency, so they can just get analog voltage out of that. Again, using smart pins as oscilloscopes, basically, to be able to see the input and output from this filter is kind of neat. So as they're increasing the resistance in this RC low pass filter, they can kind of see the carrier frequency attenuate out in this red output. So again, this is all built into this P2 chip and the Propeller tool interface, which is cool. This is exactly what I've been hoping for. All
Gavin,
right. Yeah.
is there any like pie in the sky thing that you wish it could do that it doesn't do?
Yeah, I think we can talk about this stuff later, like over the summer. But again, what I really am dreaming for the oscilloscope is being able to have virtual buttons and being able to say, okay, well, let's say I want to have the voltage per division go up or go down. And I think so. I think you've already got the infrastructure here for being able to, how to deal with the data streaming out of the smart pin. But I think we could just kind of to brighten this up and make it a little bit more user friendly and showy. So like the cake's baked. Let's just put some icing on it so it looks delicious.
You'd use plot, of course, to build all that, but you could reconstruct the oscope in using plot.
Yep. So I spent a lot of my spring break trying to build one from scratch in Plot, and then I found you'd already made the simple scope that I'd missed in one of the live forms. So I found that, and that's working great for the semester. But if I've got some time over the summer, I'd like to dig in, hopefully with your help, and try to work out a kind of a neat kind of showcase oscilloscope and again multimeter functionality. I think that'll become the backbone of how this all
Yeah.
comes together.
We got to figure out where to best divide the pie for the user interface.
But again, just having things like sprites, even though it seems like it's just for video games, I think has all kinds of implications for just making neat user interfaces. That coupled with the mouse and the keyboards. Maybe we need to make some objects that just make it very simple to draw virtual buttons into a plot screen. Or I've also kind of wondered why we need to have so many separate debugs, because it seems like everything's now getting piled into the plot. So couldn't it be that the plot could do all these things? Or
Well, what the advantage of having the specialty ones like scope and FFT and the logic analyzer is that you can feed it a very minimal amount of data and it just handles everything. So you get the highest bandwidth that way. Whereas with plot, you have to kind of micromanage everything.
got it. Okay. Yeah, I was wondering in your the keyboard, the mouse demo, I haven't really dug into a lot. You have it just plotting dots as you move the mouse around, but it seems like there's a bit of latency. Is that's kind of a result of the
Yeah, there shouldn't be. I mean, we could put a delay in there. The latency may come from like the input buffer on the PC getting bigger. You know, it's not being depleted. The data is not being utilized. So you wind up with a phase lag. So if you put like just a little pause in the loop of the drawing program, then it'll sparse out the data so that it doesn't overload the PC. Because sometimes,
oh, I see. Okay.
yeah, the PC
Cool.
will have trouble. It can receive the data and process it, but Windows takes a while to draw everything.
I see. Interesting. All right, so other things I showed off is an RGB LED. This is non-addressable, but they basically send PWM signals into it. So it kind of shows them an application of PWM. So they basically make their RGB LED turn into any color they want by adjusting the duty cycles. And then we get into H bridges and how to change the direction of a motor. So a very important concept of mechatronics. Again, I've vetted lots of different equipment. This is a very inexpensive dual H bridge that works off a much lower voltage than most of them. And so this one works, it might wind up in the kit, or there's another one that Plolu makes that I really like, a little bit more expensive. It's just a single driver. And so basically walking through how to create PWM signals to control the H bridge. And then what they do is sort of then we get into quadrant coders. Obviously a major part of mechatronics. I showed them how you could do it from scratch in spin 2 code, but really we use the smart pins. So this is just more conceptually how you could look for it to be at a certain value of the 2-bit gray code, and then how it changes, and then decide if you're adding.
Yeah, that's a great state drawing there. That really gets the gray code across.
Yeah, help them understand it. But then of course we just use the smart pins. And these work beautifully, even with their homemade ones with these little IR distance sensors and that little cheap acrylic spoke thing. It works flawlessly. And then they hook it all together to make the servo system that I was talking about. And so they have to make it so that they've got this very cheap brush motor with that acrylic disc on it. And they've got these little IR sensors measuring the spokes on the discs, and they're physically offset a little bit so they see a quadrature output. And then they build a servo system where they have to create a proportional control based off of how far from the target they are. So they'll say they're at a certain position and they want to be at a different position. Based on how far away it is, they adjust the duty cycle going to the H bridge to be able to tell how much power to put into it. So if they're very close, they're just going to tap it with a small amount of duty cycle, small amount of power, but if they're way away, they're going to floor it and go really fast. So I think there's a lot of interesting concepts in terms of mechatronics going on in just a simple system like this. And then this led them to their midterm exam, which they literally just finished at 10 a.m. this morning. And as Ken mentioned, he thought this was pretty difficult, but this is college level engineering. So what they're doing is they're building a car power window system from scratch. And so I worked this out in CAD so they could see how it works. And they were given these components to work with. So I made it a little bit difficult. I gave them a 4 relay module. And this also has some optical isolation circuitry they had to figure out as another kind of twist to this exam. And I showed them what that looked like in a Tinkercad simulation. And so these are just off the shelf parts that are pretty easy to find. And I gave them an op amp and a capacitor and some resistors and buttons. They had to figure out how to connect all these things together to make a car window system. And as a twist, I made it so they had to figure out if somebody had their hand stuck in the window as it was going up and automatically stop and reverse. So they'd So you'd write some spin code, and let me run this real quick. I'll just kind of give you an example of the sorts of systems they're building with these kits. So here's the, I'm running that code you just saw. And so they basically would have a window up and down button. They'd hit up button, for example, and it would start to spin, winding up the window until it hit the limit switch. They'd hit down and it would go until it hits the limit switch, up. It's actually a little bit up till it hits the limit switch. And then if it's going up, so down, and then up, and it actually, if it detects too much torque, we've got a little bit of a voltage on this shunt resistor going to the comparator, and it gets cleaned up by a little low pass filter. It automatically stops and reverses to go down. I'll mess with this a little bit. So this is setting the threshold. So if it crosses the threshold, it automatically reverses. Okay, so this is just an example of how they're able to make this work with the acrylic disc and the servo system. And again, what they do in the end of the lab was they were using these two IR distance sensors to make a quadrature encoder coming out of this, so they could detect how many positions it's moved through. This is kind of what we'd be doing on these kits. This is kind of just a quick demonstration of the sorts of things they build. And this is one of the reasons why we need a bigger breadboard, is we build circuits that get convoluted. All right, so then other labs that are going to happen this semester. We have a lab coming up on RC servo motors and stepper motors, and then another lab on peripheral devices, I think is what I'm calling it. So it'll be how to interface through SPI and I2C, and I think there's some other ones I might use, and then and UART, of course, and then another lab that I mentioned about having some kind of signals coming in and out and dealing with sampling and Nyquist frequencies. And then the thing I'm not 100% certain how to do yet in terms of making it low cost for a kit is some kind of a PID example where, so I just showed you an example at the end of lab 4 where they were doing a proportional control, but how to really bring in the PID. Of course, the floating point that Chip has made for us is going to be really helpful in making that come to life. And I'm looking for something kind of cool to do that. So Chip, you'd mentioned having a propeller system that launches like that toy. I've also played around with trying to have one of those, you see these in science museum shops, we've got a globe that's suspended under an electromagnet and just kind of levitates there. Trying to work out something like that is sort of an inexpensive way to be able to show how to do some sort of PID control. Of course, the inverted pendulum is kind of a go-to these days. I've seen variations of that. One example is to have a little quadcopter propeller that's on a little pivot on an encoder that basically just is trying to maintain a level, and it can go up and down with the lift. So some kind of a PID type setup that's low cost. That's my goal. And it might even just work with the cheap motor system and encoders, just having some way to do that. I've had a wonderful way of teaching it for the last couple of years where I have a really fancy industrial scale, they call it a servo motor, where it's got an analog tachometer in the back of it. So it's really nice because on oscilloscopes, you can kind of see your analog input voltage and then the analog output from the tachometer, and as they're moving relative to each other. But we can always just do that through debug windows, plot windows. Yeah, so I think that's it. I'll wrap up there. Are there any questions about kind of what we've been over and what I do?
Yes, I have a question. The little spoked disc that you put on the gear motor.
Yep.
That's aluminized. So it's reflective.
It is, but I cut them upside down on the laser cutter.
Come on in.
Hasn't been a
I
problem.
ask, how did you cut that on the laser cutter when the illumination might reflect the laser?
Yeah, it does, but I'm putting it upside down, so it's just that it's got a dull side and a bright side. So I definitely don't cut it bright side up.
Oh, okay.
So I cut it dull side down. I mean dull side up, and I'm using a fancy universal laser. It's a 75 watt air cooled CO2 one at school, but I've also got one in my basement here that's 100 watt water cooled one. But of course I use the school one because that's, not on my dime if it does screw up the laser. But that one's worked flawlessly for years. And one of the tricks is only let the students cut acrylic on it. Once you start letting them cut wood and stuff, the lenses get sooty and it just becomes a mess.
Thank you.
Yeah, good question. So my goal with these kits is to have Parallax work with some local company that can do on-demand laser cutting. So the idea is that we'd be, sending out dozens of these little boards at a time, just getting them all thrown in and laser cut, and then having some kind of acrylic plate that goes on top of these that makes it all nice. And with the acrylic plate, we can have like hex patterns for nuts cut into the acrylic. So it just you don't even need to have a wrench. You just kind of screwdriver everything in. Again, I kind of splurged on these boards that I made last winter because I really spared no expense. And so I actually used an auto tapping feature on a mill to be able to tap all the acrylic holes with threads. I had some help with from machinist and doing all that, but these really came together wonderfully. And I think these are going to last for many, many years. Any other questions?
I'll ask another question then. Who sells the little LEDs that have built-in resistors?
Yeah, I got those off of Amazon about a year ago. And so you can probably find them. I'll see if I can find a link and share it in the chat for you. Okay, and it's kind of novel. Again, I'm worried that as an educator, if I start telling students that they're out there, they're just gonna, if they learn and that's the only LED they have in their kit, they're never gonna use currently resistors, and that's obviously gonna cause problems pretty quick. But it's kind of neat they're out there. Again, they're meant to be run off of 12 volts, but they work just fine off of 3.3 volts. You don't always need to totally blind yourself. I'm also planning to put an array of RGB, addressable RGB LEDs in. So these will come way down in cost, and it's just sort of a fun way to program. So this will be in that peripheral device interface lab, just because these are so popular.
The LEDs with the resistors built in, I think they're meant for the automotive enhancing people in the world to, glorify their vehicle with some LEDs and not have to have a lot of components.
Right, and for years they've had LEDs that would come with the current limiting resistor soldered onto one of the leads, but now they've just kind of shrunk it down and stuck it into the plastic case, which is kind of interesting.
Gavin,
Right, Steve? Yeah.
in the
Go ahead,
notes, Jonathan Titus mentioned that he thought it might be valuable to introduce students to logic analyzers. Have you thought about incorporating those in your course?
Well, there's a mode in debug for that. So Chip's already worked out a debug mode that it spits everything out as a logic analyzer. So yeah, sure. To me, that's just sort of a special case of an oscilloscope. That's just only showing high and low rather than anything in between that. But you can basically use the oscilloscope functionality to do logic analyzing too. It's just usually cost as to why you buy a logic analyzer instead of an oscilloscope. And with Propeller 2, you can have a 64 channel oscilloscope. So.
Okay.
Gavin, just as an aside, I've been doing embedded systems for quite a while. And I had to do a multitasking system, a cooperative multitasking on Intel and then Motorola chips. And I wanted to know when each of the tasks were running. And by having pins monitored by a logic analyzer, and then outputting values to the unused pins, essentially to this chip, I was able to send out the different levels, and the logic analyzer would pick up which tasks were running in real time with no performance penalties. Unlike the Propeller chip, where one cog can monitor other cogs with no time dependency, doing something like that on regular processors incurs time latencies. And so I was able to do stepped logic analyzer patterns that tell you which tasks are interrupting which tasks and things like this.
And you'd actually read a
Back in
binary
the-
number coming out of the logic analyzer to figure out what it was doing.
You could look at the waveform coming out of the logic analyzer because you're watching a parallel bus, and the altitude of the waveform tells you which task is running. And so real easy to do. And then I could also dump data from the logic analyzer and feed, if you remember those old text to drawing systems, on Linux systems, I was able to then print charts as well of what the task system was doing. And so real common
Cool.
to look at things without performance penalties using, I worked for a logic analyzer and scope company, Hewlett Packard. And so this is what we were doing to study operating system I did for an optical drive and get performance numbers and things. So kind of fun, but that was back in the 80s. So now we can do it with debug displays and suffer no performance penalties either, which is kind of fun.
Absolutely.
HDMI for performance monitoring and then debug displays for monitoring with lag, but kind of fun.
All right. Well, I think you're up next, Stephen. So sorry if I've taken up too much time, but
Yeah, that's great.
No, Gavin, that's awesome stuff.
And then
yeah,
Gavin,
we're having fun. I'm still in the thick of it for another 6 weeks, but then hopefully I can figure out how to turn this all into something that Parallax can get out to the rest of you.
I'm looking forward to it. And Gavin, I want to thank you too for letting me play along with your students because it's a great refresher for me and it happens to feed the work I'm doing. But it also motivated the next thing I'm going to show.
Awesome.
So
Cool.
if that's okay with you, I'll do that. And so I'll share a screen here. If I can find out which screen I should be sharing. Too many windows open. All right, here. I think it's this one. It is. Okay, good. So you might recognize these displays. I'm showing Visual Studio Code Editor, Gavin, where you're doing everything in Propeller tool. And so what I'm doing is the semantic. This is syntax highlighting and what we get out of it. And if I switch to semantic highlighting, which anybody who has Visual Studio has the themes to cause this to happen, I can switch over to the non-syntax one. And this is what the debug displays now look like under Visual Studio Code. And so here you see I'm defining a scope and I'm naming it and I'm defining the channels on the scope, naming the channels, scaling, and then colorizing the lines. Use your triggering information. Then I'm defining some terms here, terminals. And then here I'm feeding data to them. These are the examples from the Spin 2 documentation, so we could see what they'd be colored like. It's more than just coloring. This is validated by the type. And so if you define a scope and try and put something in here that's not related to the scope, you can see that I'm going to tell you that I don't know what it is. And so rather than learn this at compile time and have Propeller tool or Peanut tell you that it doesn't compile, you can actually tell right here that it's just not spelled correctly or it's not known by this display. And so we're
Stephen, think if they had like allowances for like flashing colors.
Yeah, I don't want to go there. I just simply like background colors and they don't give me that either. But anyway, you can see what's happening here. And so this is the scope display with highlighting. Again, another scope. This is the term display. This is the logic analyzer with highlighting. And so all of the displays now in the debug displays. And so Gavin, I say you motivated me because in your examples, I'm having to do a lot of these displays with the debug displays. And I wasn't getting any syntax highlighting or validating that I'm spelling things correctly and things like this. And you just really kind of want that thing. And so it tells me as I'm writing it, that I'm writing it correctly. And so these are then where we are. Colors are marked separately. So you can see where you have colors in the text. I may change this. I may add this also for color modes. I think Lumax 8 is a color mode. Here's your plot display with strings. Part of what made this entertaining for me was Chip introduced single quoted strings, which moved the single quote out of the syntactical space into semantic space. And so I literally had to turn off single quoted strings as a syntactical behavior because it would take the entire right edge of these lines and decide they were line comments. Syntax is not context specific in their parser. And so this is all working. Here's your bitmap display and the validations you get. And the one thing Chip headed me towards is we can do runtime determination of display names. And so I can never know from a code parser what this display would be or how to validate it. And so what I'm proposing, if this group likes it, is I'll support directives in front of it where you can say that either everything in this file from this point forward or the next line is now to be validated as this display type. And so in the next release, not this one, I'll have these support for directives that will help the validator understand that this should be a keyword that's known by this display. So that's the new addition to the VS Code highlighting syntax extension that I just released yesterday. Everybody has. Does that make sense? Anybody have questions over this?
I can get her at 4.
Looks great.
So anybody that's running VS Code probably has this automatically downloaded.
4 p.m. pick up Summer.
I do have.
Okay, so 4 p.m. Brendo's. Okay.
I as I'm running now,
All
and as I'm seeing some things I want to correct, and I also want to put in the support, and so I'll be following this very quickly with another
Okay,
release,
Summer. Okay, no, I'll do
just
it.
to fix other things up.
All right. Thanks for
Which
your
will
help.
add
See you in
the
a bit.
override.
Okay, bye.
So that's what we have. I would like to put in a plug for saying that if anybody is using VS Code extensions and sees code that's not highlighting correctly, that they think is not correct, direct message me and send me the code or file an issue at the repository website with the code. And every time I get examples that are not highlighted correctly, I add it to my test pool, and then I will fix them in the next release. So please contribute anything you find. And that's all I have.
Thanks, Stephen. That looks super duper.
But kind of fun. There was a question I had for Chip.
So there's no allowance for background color in that?
No, there isn't.
Because
No,
they use it for highlighting or for selection.
Yeah, well, I don't know why they don't offer it, but if they did, I would have probably mimicked Propeller Tools interface a little bit with coloring sections, but I just can't. It's not available to us. I basically studied everything we could do, and then I've been gradually making use of it over time. And so we will see tabbing that works exactly like Propeller Tool. We will over time be able to do code formatting. You can imagine that's a risky thing if we do that wrong, because it changes the meaning of the language.
Right, right.
So that has to be done very carefully. But it would align up columns of your assembly language code, your conditionals, your flags, things like this, based on the user settings, just like Propeller Tool. Propeller Tool allows you to move things into the right columns. This would actually do it for you by understanding the language.
So I'm still a little confused with the overview, Stephen. If you can explain, so I understand Visual Studio is working this out, but then how are you going about compiling the code down into the Propeller 2 chip?
Oh, you'll like this. If you're running Visual Studio on a different machine, then you have to share a file system of some sort, like Dropbox or iCloud storage, whatever you want there. If you're running on the same machine, then you just have Visual Studio storing into a place that's known by Propeller Tool and have Propeller Tool pick up the code. In my case, I'm running on Mac desktop. And so I have an emulator that is free, provided by Oracle. And I can show you what this thing runs like. It's pretty much indistinguishable from It's called VirtualBox. It's pretty much indistinguishable from running Windows for the purpose of running this tool. And so I'm running on a Mac. I will now see what I can do here. Hello. Great. Just hide all my share screen controls. That makes it easy for me.
Okay.
Here you see the emulator starting. And I'm running on a, what, 18 core Mac. And so, or 12 core, 14 core, I don't know. I've got a number of multi-core Macs. And even that takes time because we're running Windows on a Mac and a Mac file system. But what happens here then is you'll find this is almost indistinguishable from it running in a Mac. Because it's running in an emulator, I can say this part of the file system is shared between the Mac apps and the Windows environment. And then I can run Visual Studio Code on the Mac itself natively, point it to the file system that we're sharing, and then Prop Tool sees that code and loads it. And they're immediately saved. There's no delay like with Dropbox. And so you can run the entire tool set on the Mac with free tools, including the Windows operating system is free. Windows 10 has a free version that you can use, which renews like every 90 days or something. So here I am running the free version, taking a little bit of time to start. Propeller tool. And of course, I don't have anything that any of your examples set up on the hardware, so I can't run against hardware right now. But you'll see your code. And it's very, once it's all up and running, it's very practical to run. It's the startup that's pretty slow. And so waiting for Prop Tool, there it is. Propeller tool is started. I'm running a 2.7.0 beta. And here it is. And I point it to, I literally define a drive that is the share. And then I have code that I've written for your different examples. And you can see then that I'm just running your code. The same code then in Visual Studio. Right. Come on. So you can see what they look like. And so I tend to prefer Visual Studio for editing because I do a lot of development. And so for me, I prefer not to have to switch between Prop Tool and this. There we go. So I'm going to minimize this one, start this one. Okay. And then change my share. So this is what it looks like in the Windows instance. And I can show you the same code then here. We were just looking at this code. So you can see the code looks the same, except for now it's colored by Visual Studio. Oh, look, I missed an operator. And so when my syntax highlighting is wrong or doesn't know something yet, I get these wonderful red flags. And then I go in and update the extension, and now I know I've supported that. So all my test code. So then here's your digital logic example. So straight out of, right, here's the waveform you set up. And so you can see we've got a syntax problem here. It's not coloring correctly. And so I run with this, and this helps me validate my tool set as well as do your work. And so your question is, how do I do it? I have two large screens sitting side by side. I have Visual Studio handling one of the large screens, and I have the Windows emulator running on the other screen, and I edit one window and run from the other window. So real common. When I'm running on Raspberry Pi, it's the same thing. I'm running FlexSpin on the Pi. I'm running Visual Studio on my Mac. Visual Studio remotes automatically into the Raspberry Pi. where it's running an instance over there. And so technically I'm editing on the Raspberry Pi and downloading with FlexSpin on the Pi when I'm running Visual Studio remotely. I can do the same thing with Windows. When I'm developing a motor driver, I have a Windows machine driving connected to the robot. I'm editing on my Mac, the big driver code. And in that case, I'm running Visual Studio, saving to Dropbox, allowing the couple seconds for transfer of Dropbox the changes to the Windows PC, and then building and downloading with Propeller tool on the Windows PC. So in my house here, I'm running in like 5 different configurations of shared file systems and tools on either end of the share. But it's almost always Visual Studio Code for me. And so your work then motivated me to just extend that syntax highlighting to the new pieces of the new area of the code that you have me working.
Yeah, this is fantastic. And I see this really helping people that are coming from the Visual Studio background that want to get into the Propeller tool, just having a great time in their home environment.
Exactly. And so it's really you've seen the Raspberry Pi 400s, I think they are. That runs Visual Studio and that runs FlexProp. And so having the P2 connected to this little portable thing and
This is the little white keyboard one.
Yeah, having all your development tools right there, running Visual Studio, running FlexProp, or even running FlexProp interactively with its own editor, and downloading to the P2, that all works beautifully. I think Avi has one right there.
Yep.
Yeah, and so that you put a display on that, run all the code right there, and you're good to go. Connect your P2 environment.
Yeah, so Chip, that is what you've been alluding to making with the P2. So this is with the Raspberry Pi 4. It's the keyboard that it's just built inside the keyboard case, and it has an HDMI out.
Right, and so the difference is in that environment you lose the advantage of having the debug displays and things because those are Windows native compilation tools, and so then we have to have some sort of Windows environment to do that. I haven't tried yet. They threaten that this VirtualBox that I'm using may run on Linux as well. And if it does, that suggests that with a sufficient Pi-like type box, you might be able to run the whole Windows environment. But to me, that would be totally challenging for a system that size in my mind's eye. So I don't know how well that would run.
Hey, Stephen.
Yes.
In your code, is your code running all the time? It kind of is, right? Because it can change like schemes based on what the user enters. So your Visual Studio configuration code is running, right? Or could you not, or did you not say it's running?
It is running live and it reruns the entire system with every keystroke.
Yes, okay. So you know what? You do have some handle on time then, potentially, right?
What do you mean time?
Is there any facility in that system for figuring out like how much time has elapsed since you last went through your loop? Or does your code just run upon keystroke?
My code lives in an environment where it registers itself with the Visual Studio Code application. And Visual Studio Code sees something going on, knows that it happens to have a spin2 file loaded, and then invokes my code at the time whenever it sees a need to have something changed.
Okay, whenever it sees a need.
Correct. I'm not in control whatsoever.
I see. I see. Because
I'm a delegate task that gets run only when it sees the need to.
right. Because I was thinking if you could run like always or preemptively in some way, you could get a handle on time and then actually make like blinking. You couldn't control background, but you could do like real-time blinking.
Yeah, no, because we're a client, we are required to be a well-behaved client.
Required to be a what?
A well-behaved client, meaning
Right.
be respectful of processor time. If you look at my environment and the number of extensions I have loaded, for any one file I'm editing, I could be running 10 or 15 different extensions. Some of them are looking at matching braces and parens and square brackets.
Right.
Some of them are spell checking, some of them are, looking for errors and then reporting errors, that they all independent of one another. And so each of those extensions is given time to look over your file. If you were to dominate the time, everything else runs slower, it doesn't get a chance to report at all.
No, yeah, you wouldn't want to dominate it, but if you could get a call at like 10 times a second or something.
Yeah, you've got no control over that whatsoever.
Yeah,
And
I
so
see.
as we build our extensions, we study the context in which we're run. And we're only allowed to do things that the developers have say that it's important for us to be able to do.
Right.
So if you look at the sheer number of lines of code, this is TypeScript code, which is JavaScript with strict type checking. So TypeScript, it's JSON files describing how things are working. It's YAML files that describe the syntax for syntax highlighting. So it's a blend of a whole bunch of different languages, all compiled and incorporated into an extension, which has a description file that says, here are the parts of the extension that provides. In my case, it's a couple themes, and it's the TypeScript extension for highlighting. Once we have the tabbing, it's an outline extension also, so I recognize where the pubs and pries and cons and dats and vars and things like this are in the file, and feed that to the outline display mechanism. So there's just a whole bunch of parts that all have to be well behaved. It's fascinating if I do something wrong in the code and something loops, because the whole system just stops.
Right, right.
So you learn when you're ill-behaved very quickly. And then
And
you
you
back
can't
up and move forward again.
You can't set any kind of timer for a future event or to even trigger what looks like a keystroke or anything, like a change of the shift or control key.
No, I have no ability. It's all an external. I'm just a client within the system. So there are Pascal clients, there are COBOL clients, there are C, NCC, C++, Python, you name it, the clients are all there. I'm just a Spin2 client, Spin2 and PASM.
So it's sort of a don't call us, we'll call you situation.
Exactly. I'm limited to the services they provide. They do occasionally extend the services. And so I could imagine that they might give us better highlighting or coloring in the future, but who knows?
Right.
And this is a Microsoft developed platform, I believe, Visual Studio Code. And they offer it as open source, which is intriguing. But yeah, fun questions. Question for you, Chip. How do I, one of the examples, do I even have it available anymore? I just hit it actually. How do I know if we are, you have two different types of display keywords. I'm trying to pull up the display here.
Well, yeah, there are, let's see, how would you qualify those? There are those that it looks for and then those that you introduce, right?
Well, there's a different way of putting it. In your Spin2 documentation, one is like instantiation and the other one is feed.
Oh, okay, right.
But there's not a good technical way to distinguish between the two.
Because some keywords could be used in both places.
Correct. And so by looking at keywords, I can't tell which is which.
Like update.
Right. And so the challenge for me, and I'll show you, why do I keep hiding my own screen buttons? I like interfering with myself, apparently. So let's take this case. This is instantiation here. Can you see this okay?
Yep.
Okay. As is this, as is this, as is this is feed. So I can't tell if this is instantiation. I know that this is because I have this pattern.
Right.
I can't tell that these are unless I just look at keywords and see if it is. But then keywords lie.
Yeah, I mean, there could be, the thing could even maybe instantiate the backtick. I mean, it could at runtime generate the backtick character potentially too, right?
Yeah, but I won't be able to recognize that. As
Yeah,
I have no ability to recognize anything at runtime. This is only
right.
semantic.
Yeah, there's some stuff that you just probably won't be able to
Right. And so
highlight with any determinacy.
the way I solve this then is I just basically do a union of the two sets
Okay. Oh, yeah.
because I have no way of knowing. So I look first in instantiation keywords. If it's not there, I'll feed it. I'll hand it to feed keywords. And that's all. That's the best I can do as far as I know. So for the instantiation ones, I limit it to instantiation. So I just want to double check with you that I'm not going awry by doing that.
No, yeah, there's not much you can do about that.
Okay. Cool. All right. I think I presented everything I can.
Super. It looks really good.
Unless anybody has any questions, that's all I have. Oh, I did find, if you saw the motor demo video from last week, you saw that when I slowed down the motors, they were slamming. I found the code problem that was doing that, and kudos to Chip for doing inline PASM, because I literally took small PASM sequences that I was doing in the driver, embedded them in line, and then put debug statements fore and aft, and just iterated over them with values that I was going to pass to the driver, and watched what the PASM code was doing, and found that I had done some carry flag comparisons backwards. And so it was slamming the values instead of ramping the values. And so very nice way to find things. And so I've been proving out the driver because it's so hard to diagnose with the motors in place and running. I've been proving snippets of the driver segment by segment, proving that the code works so it's known good by the time I put it in the driver. So I've got 4 more segments to do, and then I've got a fully certified driver at this point. So thank you for giving us that feature. That's been wonderful for unit testing code.
Oh, yeah. I noticed a problem, Gavin. I don't know if you've run into it yet, but you know, PC mouse and PC key. I have 2 separate parsers. One does the assembly language version, like if you put the debug in the PASM code and you put statements, separate code from what compiles the debug statement in spin2 code. So anyway, I totally wasn't even looking for PC key and PC mouse in the PASM compiler version, so it wouldn't have done anything. But I fixed that. Jeff might have added it into the last one if he just published something. But
Yeah, I
you're
haven't
right.
taken it. I haven't worked with PASM at all yet with the
Yeah,
mouse and keyboard. I don't really expect to need to, but maybe if I get to a finalized kind of interface for the oscilloscope, I think PASM, again, if you can help us work out some PASM objects that are just kind of amazing for some of these backbone sort of functionality, that's really cool. Again, I'm hoping that eventually the dust will settle enough, Chip, you get to spend some time writing some programs on this chip that you've created to just pull out all the stops and make it do some amazing stuff.
yeah, there's everything there to do a GUI now. It's just,
So I can make one that's kind of in spin2 that's going to be a little kludgy, but if you could make some stuff that's just running an assembly in the background, I was thinking about this too, is that for the types of stuff we're doing in mechatronics, we don't really use all the cogs very often at all. So having just dedicating one cog to just take care of all the GUI and the oscilloscopes and stuff really isn't a big deal.
no,
Especially if it's just running assembly.
Yeah, no, that wouldn't be a problem. All right. Yeah,
Gavin, that's one of the things I did with the HDMI display, is I needed real-time output from what my other cogs were doing. And so I had each of the cogs that wanted something displayed just ship off a display list to the display cog. And then every time a new list came in, it just added it to its list, and the display cog would just sit there, iterate over everything that was going. The display list had 2 components, which elements are static and which elements are live. And it would paint the static stuff once and then iterate over the live stuff. And some of my displays were really fast. And so I was watching motor control variables update in real time. and this kind of thing, and know when things went awry, when a fault occurred, I knew immediately. There's no delay as you're shipping the stuff over the serial port for debug displays. And so that was real easy.
Yeah, that's good use. See, if we put tools on the chip, everything would be that way. It'd be like super real time. The trouble is the necessity of extra displays and input devices.
One of the things I was doing on the P1 was exactly the same thing. My display list was, what data structures do you want to see? And I was literally watching things in hex being manipulated real time on the P1 display. But I was using 3 cogs to generate the video at that point. Now we're using so much more effective on P2. I have much more resource available to do other things.
Yeah, yes. I was going to put in the debugger. I'm thinking about doing it kind of like when something changes. If I can, I'll do this later on, but if I can have histories of like what has been in each of the registers, then anytime a change occurs, I can set like a timer for that digit even. And like, boom, it goes bright red and then it fades to like the normal background color. You know, as it iterates with the callbacks from the P2, it could drop that counter down, and then so that way anytime any data changes, any bits or nibbles, you'd see it go red and then it would kind of fade away. I can't just have it go red and then go plain when there hasn't been a change, because what happens is if it's doing this 16 times a second, you're going to miss it. You're going to see a blip, but if you like make it bright red, then fade it down, and anytime it changes again, make it bright red again.
That's just a runtime display list.
Yeah. Okay. Yeah.
Processor. The display list adds it. It has a countdown as an entry, and once the entry counts down, you remove the entry.
Yes.
This could be done on the PC debug side though, right? So that maybe just have an extra parameter that's specifying the intensity or something.
Yes.
Yeah, no, the PC would handle all this stuff.
Okay.
Because it's dealing with like very seminal data that doesn't have any awareness of any of this stuff. You know, it's just what's in registers.
That's a single display blob too, which says, you know, this piece changed, highlight it for this many counts, or count
Yeah.
it.
Yeah, you could run that.
Highlight it with this color and then count it down, and it would do it all itself once you told it to change.
Yeah. Yeah, you could set that counter to 20 or so, and then over 20 updates, it could run all the way down to 0 and stay at 0. You could use that as like have a level detector, when to go from highlight to not, or you could use it to analogically fade down. The analog fade down might be kind of cool looking.
That's kind of similar to what they were doing at the time of flight display that we saw.
Yeah. Oh yeah, yeah, same kind of thing.
Yep.
Yep.
Just highlighting change with the important pieces.
Yeah.
Interesting.
All right, Chip, I think we are going to general discussion, so you could stop the recording and.
All right, I see Mike Summers not here. So if I stop the recording, let's see, where do I put, where is the recording here?
Oh, what's Gavin got here?
Oh,
Oh,
stop
LED.
recording.
He's playing with LEDs now.
Oh, that's cool.
That's the LED panel.
Nice.
It's stunning what we can do with the P2 and these LED arrays.
Okay, I'll stop recording.
Hey, Gavin. This was a P1 with a Bluetooth interface. That's the where Bluetooth chip, P1, LED panel. So you can literally drive the panel from an iPhone over Bluetooth. So that was P1. That was what, 7 years ago I was doing that kind of stuff. But yeah, I
Wow.
love this kind of stuff. But the P2 makes this stuff so much easier now. And so having this in your course where they're playing with that kind of stuff is just amazing.
Yeah, so this RGB LED array is definitely,
I lost your audio.
it's going to the next lab. So this one's gonna be coming up for in 2 weeks. I'll send you the the code for it.
Yep.
But again, these have just become so popular, just it makes sense to throw these in. They're just really fun to work with.
Really does.
They're like an 8x8 array.
Yeah, 8x8 array. Everyone can be.
And addressable.
Excuse me.
Yep.
Excuse me. Hello? Hello?
Hello.
Yeah, Enrique.
Please excuse me, but did you notice that the recording is still in progress?
It's,
Zoom did
yes,
not
hang on.
acknowledge the stop
Okay.
recording.
I think it's, yeah, it might be.
At the left upper side of the screen.
Yeah, I'm pressing the button, but it's not stopping.
Great.
Yes, because I ever heard the Zoom speaking recording stop it when you choose, and perhaps there is some failure or a version mismatch. Because for example, my version of Zoom was updated just today when I entered the presentation. But perhaps